Imagine stepping into a time machine capable of transporting you back billions of years, allowing you to witness the birth of stars, the formation of galaxies, and even the dawn of the universe itself. While a literal time machine remains beyond our grasp, humanity has developed something nearly as extraordinary: the James Webb Space Telescope, or JWST. This state-of-the-art marvel serves as a powerful window into the distant past, peering back an astonishing 5 billion years, nearly to the very moment the universe was born. The JWST is transforming our understanding of the cosmos in ways once thought impossible, offering a glimpse into the universe's earliest moments and unraveling secrets that were previously beyond reach. But to truly appreciate the magnitude of what this telescope can do, we first need to understand the origins of the universe itself, the Big Bang. The Big Bang wasn't an explosion in the traditional sense. It wasn't a massive bomb detonating in space. Rather, it was an incredibly rapid and profound expansion of the universe from a single point of unimaginably dense and hot energy. This monumental event, which took place around 8 billion years ago, marked the birth of space, time, and all the matter that exists in our universe today. The first moments after the Big Bang were a chaotic, superheated ocean of energy and tiny particles moving uncontrollably. The universe was so hot, trillions of degrees, that atoms couldn't form, and there were no stars or planets for hundreds of millions of years. For a vast stretch of time, the universe remained in this dense, glowing state, gradually cooling and expanding. Then, around 400 million years after the Big Bang, a profound transformation began to unfold. Gravity started pulling hydrogen and helium, two of the simplest and most abundant elements in the universe, together, forming the first stars. These stars began to cluster, giving rise to the earliest galaxies and lighting up a universe that had once been entirely dark and featureless. This remarkable period in cosmic history, known as the Cosmic Dawn, is precisely the era that the JWST is now uncovering. It is capturing images and data from a time when the very first galaxies were beginning to shine, offering us a window into the universe's earliest and most formative stages. The JWST, which launched on Christmas Day in 2021, is a technological marvel. Positioned 1 million miles away from Earth at the second Lagrange point, L2, it orbits the Sun in a special location that allows it to remain in a stable position, shielded from Earth's heat and light. This unique vantage point gives the JWST an uninterrupted and incredibly clear view of the cosmos. But it's not just the telescope's position that sets it apart. It's its groundbreaking ability to detect infrared light. While most telescopes rely on visible light, infrared light can pass through the thick dust and gas that often obscure our view of distant objects. More crucially, infrared light is essential for studying the oldest stars and galaxies. As the universe expands, the light from distant celestial bodies stretches into longer wavelengths, shifting from visible light into the infrared spectrum. This process, known as cosmological redshift, occurs the farther away an object is, with its light becoming more stretched out. Because the JWST is designed to detect these faint, stretched-out signals, it can peer farther back in time than any telescope before it, unlocking the universe's deepest secrets. In essence, the JWST acts as a time machine, enabling us to see the universe as it was 13.5 billion years ago, just a few 100 million years after the Big Bang. With this ability, the JWST isn't just capturing breathtaking images of the cosmos, it's revealing the building blocks of our universe. It is providing unprecedented insights into the birth of stars, the formation of galaxies, and the very origins of our cosmic history. When the JWST sent back its first images, scientists were left in awe. The telescope had peered deep into the universe's past and captured something truly remarkable: galaxies forming just a few 100 million years after the Big Bang. This was a time when the universe was still in its infancy, and yet what the JWST revealed was a cosmos teeming with activity. Astronomers had expected to find only a handful of early galaxies, but instead, the JWST uncovered far more than anticipated. Not only were there more galaxies than expected, but they also came in a variety of unexpected shapes and sizes. This discovery suggests that the young universe was far more active and dynamic than scientists had ever imagined. One of the most extraordinary revelations was the detection of proto-galaxies. the very first clusters of stars that would eventually merge to form the massive galaxies we see today. But these proto-galaxies were not the neat, orderly structures we associate with modern galaxies. Instead, they were chaotic, clumpy, and irregular. Stars were forming at an astonishing rate, igniting in rapid bursts and challenging previous ideas that galaxy formation was a slow, gradual process. The JWST's findings indicate that the birth of galaxies was far more violent and fast-paced than previously believed, reshaping our understanding of how the cosmos evolved in its earliest days. But the discoveries didn't stop there. The JWST is also uncovering some of the universe's first stars, known as population 3 stars. These ancient behemoths were unlike any stars we see today. Born from the raw elements left behind by the Big Bang, primarily hydrogen and helium, these stars formed in a universe that had never seen metals before. Unlike modern stars, which are made up of heavier elements like carbon, oxygen, and iron, population 3 stars were composed almost entirely of the simplest elements. Scientists believe these early stars were massive, far larger than our sun, and burned incredibly hot and bright. With no heavier elements to slow down their fusion process, they burned through their fuel at a furious rate, living short but dramatic lives. When they eventually died, they exploded in supernova, some possibly even triggering rare and extraordinarily powerful events known as pair instability supernovae. These violent explosions scattered newly formed, heavier elements throughout the universe, gradually enriching space with the building blocks needed for the formation of new stars, planets, and even life. Through these discoveries, the JWST is giving us a glimpse into the universe's evolution from a simple, element-poor state to the rich and diverse cosmos we see today. By unveiling these long-extinct stars, scientists are piecing together the story of how our universe was shaped, how it transformed from a hot, chaotic cloud of particles into the complex, structured system we inhabit now. The James Webb Space Telescope is not just a tool for stargazing. It is rewriting the history of the universe, one discovery at a time. The mysteries of the universe have long captivated human curiosity, pushing us to explore its origins and uncover the building blocks of everything that exists, from the air we breathe to the very atoms that form our bodies. But with the advent of modern technology, we are now standing on the precipice of unraveling the deepest secrets of the cosmos. One of the most remarkable tools in this journey of discovery is the James Webb Space Telescope, JWST. This technological marvel is not only expanding our knowledge of the universe's past, but it is also helping us to understand some of the most profound and enigmatic phenomena that govern the universe. At the heart of these discoveries lie two of the greatest cosmic mysteries: dark matter and dark energy. Together, these invisible forces make up roughly 95% of the universe, yet scientists still struggle to fully comprehend their nature. Dark matter, which cannot be seen directly because it doesn't emit light or energy, remains one of the most elusive aspects of the cosmos. However, JWST's advanced technology is providing groundbreaking insights into this invisible force. The telescope is able to detect dark matter by observing its gravitational effects on light, a phenomenon known as gravitational lensing. As light from distant galaxies passes through areas where dark matter exists, it gets bent and distorted. This allows astronomers to map out the hidden presence of dark matter, providing clues about how it shapes the structure of the universe. Dark matter acts as a cosmic skeleton, silently influencing the formation and evolution of galaxies over the course of billions of years. While dark matter remains a puzzle, dark energy presents its own set of mysteries. Dark energy is the mysterious force accelerating the expansion of the universe, pushing galaxies farther apart at an ever-increasing rate. By observing the motion of galaxies using JWST, scientists are able to gather crucial data about dark energy's effects on the cosmos over time. This has profound implications for our understanding of the universe's future. Will the universe continue to expand indefinitely, slowing down over time, or will it eventually collapse back in on itself? The answers to these questions could reshape our understanding of the cosmos and our place within it. Looking back in time is one of the JWST's most powerful abilities. The telescope provides a window into the early universe, allowing us to see galaxies and stars as they were just a few 100 million years after the Big Bang. However, JWST is not solely focused on the past. One of its most exciting tasks is to explore the possibility of life beyond Earth. The telescope is hunting for exoplanets, planets that orbit stars outside our solar system. Some of these distant worlds may have conditions conducive to life, and JWST's sophisticated instruments are capable of analyzing the atmospheres of these planets. By studying the chemical makeup of these atmospheres, scientists are looking for signs that life might exist elsewhere in the universe. If the telescope detects water vapor, for instance, it could suggest the presence of clouds and possibly even rainfall. The detection of methane could indicate biological processes, perhaps even microbial life. Similarly, the presence of large amounts of oxygen might hint at plant-like organisms producing it, just as photosynthetic life does on Earth. The possibility of discovering extraterrestrial life, whether in the form of microorganisms or something more complex, is one of the most profound implications of JWST's findings. Such a discovery would alter everything we know about our place in the universe and our understanding of life itself. While JWST is making strides in answering some of the universe's most pressing questions, it has also challenged existing theories and forced scientists to rethink fundamental aspects of cosmic evolution. One of the most surprising revelations has been the rapid formation of galaxies in the early universe. According to existing models, galaxies were expected to form slowly over time, gradually building their structure. However, JWST has captured images of fully formed galaxies that appear much sooner than anticipated. Some galaxies are already well developed just a few 100 million years after the Big Bang. This suggests that galaxy formation may be far more complex and rapid than previously thought, forcing astronomers to reconsider their models of cosmic evolution. Another shocking discovery made by JWST involves the size of black holes at the centers of these ancient galaxies. Current theories predict that black holes should be relatively small in the early universe, given the limited time available for their growth. However, JWST has detected black holes that are far larger than expected, raising questions about how black holes form and grow in the early stages of the universe. These unexpected findings suggest that black holes may form and expand much more quickly than our current understanding allows. As a result, scientists are now questioning some of the most fundamental ideas about the early universe, and they are beginning to reconsider how black holes play a role in shaping the cosmos. Despite these surprising discoveries, JWST is still only scratching the surface of what the universe has to offer. Its enormous gold-coated mirror, spanning more than 21 feet across, allows it to capture the faintest infrared light from distant parts of the universe. The mirror is made up of 18 hexagonal segments that unfold once the telescope reaches space, creating a stunning pattern that resembles the petals of a flower opening. Beyond the mirror, JWST is equipped with a suite of advanced instruments, including powerful cameras and spectrographs capable of analyzing light from stars and galaxies billions of light years away. These tools allow scientists to perform cosmic archaeology, breaking down the light from distant celestial objects into its individual components, revealing critical details about their composition, movements, and much more. JWST's observations give us a rare glimpse into the history of the universe, uncovering the faintest traces of light that have traveled across time and space for billions of years. The incredible discoveries made by JWST are a testament to the power of international collaboration. While NASA led the design and construction of the telescope, two other space agencies, the European Space Agency, ESA, and the Canadian Space Agency, CSA, played pivotal roles in ensuring the success of the mission. ESA contributed vital scientific instruments, while CSA provided both technology and funding. This collaboration demonstrates how scientific progress can bring nations together, fostering a global sense of unity in the pursuit of knowledge. JWST serves as a shining example of what humanity can accomplish when we work together toward a common goal, and it represents a significant milestone in our quest to explore the stars and understand the cosmos. Looking ahead, the future of space exploration is filled with promise. JWST is just the beginning, and it will continue to inspire future generations of scientists, astronomers, and explorers. Its groundbreaking data will be studied for decades to come, and its discoveries will continue to shape our understanding of the universe. But there are even more missions on the horizon. The Nancy Grace Roman Space Telescope, for example, will give us an even deeper look into the cosmos, while the European Extremely Large Telescope promises to offer sharper views of distant galaxies and stars. Together, these observatories will complement each other in unlocking more of the universe's hidden secrets. These advancements are not just about science. They are about connecting with the very essence of our existence, helping us understand our origins and our place in the vast, infinite cosmos. As we push the boundaries of what we know, we are reminded of how far we have come and how much further we have to go. The James Webb Space Telescope has already opened up a new chapter in humanity's journey of exploration, and the possibilities for future discoveries are endless. One of the most profound aspects of this exploration is how it allows us to peer back in time. By looking at distant galaxies, JWST lets us witness the universe as it was 13.5 billion years ago, giving us unprecedented insight into the formation of stars and galaxies. Every piece of data it returns is like a treasure, a rare glimpse into the early days of the universe. As we continue to explore the farthest reaches of space, we are uncovering the complex, fascinating history of everything that exists. The James Webb Space Telescope is more than just a scientific instrument. It is a time machine, a storyteller unraveling the narrative of the cosmos. And as we gaze into the infinite depths of space, one thing is certain: the adventure has only just begun. High redshift galaxies serve as time capsules that offer an incredible glimpse into the distant past, allowing astronomers to study the early universe in ways previously unimaginable. These galaxies are not just distant objects in space, they are windows into a period long ago, a time when the universe was still in its infancy, only a few 100 million years after the Big Bang. To observe these galaxies, astronomers rely on some of the most advanced telescopes ever built, such as the Hubble Space Telescope and the James Webb Space Telescope. Equipped with highly specialized instruments, these telescopes can capture incredibly faint light emitted by galaxies located billions of light years away. The faintness of this light is a direct result of the immense distances between us and these distant objects, and it takes years of careful analysis to unlock the information it carries. When astronomers study the light from these high redshift galaxies, they focus on a key characteristic known as redshift, the stretching of light waves as they travel across the expanding universe. The more stretched the light, the greater the redshift, which corresponds to the galaxy's distance from Earth. Essentially, the greater the redshift, the further back in time we are looking. This phenomenon occurs because the universe has been expanding ever since the Big Bang, and as light from distant galaxies travels across the cosmos, it gets stretched out along with the space it moves through. As a result, light that we observe today from a galaxy billions of light years away is light that was emitted billions of years ago. The more we look into the universe's depths, the further back in time we are able to see, offering us an extraordinary opportunity to study the universe in its early, more primitive state. The light we observe from these distant galaxies is more than just faint photons. It holds the secrets to the early stages of the universe's formation. These distant galaxies, much smaller and less developed than the massive, well-organized galaxies we are familiar with today, offer scientists a rare look at what the universe was like before stars, galaxies, and clusters had fully formed. At the time these early galaxies were forming, the universe itself was still a chaotic and largely uniform expanse of gas and dust. Through high redshift galaxies, we see systems that were actively gathering gas, forming stars, and undergoing dramatic changes that would eventually give rise to the large, complex galaxies we observe in the present day. Unlike the smooth, organized structures of modern galaxies, early galaxies were often smaller, irregularly shaped, and much less defined. These galaxies did not yet possess the intricate structures we associate with mature galaxies today, such as well-defined spiral arms or elliptical cores. Instead, they were often in the process of merging with or colliding into one another. These collisions were not random events, but pivotal moments that played a crucial role in shaping the galaxies we recognize today. The impact of these interactions sparked bursts of star formation and accelerated the growth of the galaxies. Essentially, the tumultuous events that defined the early years of the universe laid the groundwork for the more stable and structured galaxies that would eventually dominate the cosmic landscape. One of the most exciting aspects of studying high redshift galaxies is the opportunity to observe the birth of the very first stars, known as population 3 stars. These stars, which are thought to have formed shortly after the Big Bang, were unlike anything we observe in the universe today. The early universe was predominantly filled with hydrogen and helium, the simplest and lightest elements. Over time, gravity began to pull these gases together, eventually creating dense regions that would collapse to form the first stars. These population 3 stars were vastly different from modern stars in several crucial ways. For one, they were much larger and hotter, burning through their fuel at an incredible rate. Unlike today's stars, which are made of a variety of elements like carbon, oxygen, and nitrogen, elements crucial for life, population 3 stars were composed almost entirely of hydrogen and helium. Their massive sizes and rapid burning rates meant that they had relatively short lifespans, ending their lives in cataclysmic supernova explosions. When these early stars exploded as supernovae, they unleashed tremendous amounts of energy, creating heavier elements like carbon, oxygen, and iron. These elements would later go on to form planets, stars, and eventually life itself. The explosive deaths of population 3 stars were essential moments in the history of the universe, as they initiated the process of chemical enrichment, an essential step in the formation of life and the complex structures we observe in the universe today. These first stars were the building blocks that paved the way for all subsequent cosmic evolution. Moreover, studying these distant galaxies gives scientists a clearer understanding of a key moment in the universe's history known as the reionization epoch. This was the period when the universe, once dark and opaque due to the dense clouds of gas that filled it, became transparent. The first stars, when they began to shine, emitted radiation that interacted with the surrounding hydrogen gas, ionizing it. This process made it possible for light to travel freely through space, allowing the universe to gradually transition from a foggy, impenetrable state to the clear, transparent cosmos we observe today. The reionization epoch was critical for the development of the universe, setting the stage for the evolution of galaxies, stars, and eventually life. In essence, high redshift galaxies give us a unique way to peer back in time, not through some fantastical form of time travel, but by observing the light that has been traveling through the universe for billions of years. As light travels across the vast distances of space, it carries with it information about the conditions, events, and structures that existed at the time it was emitted. By studying this ancient light, scientists are able to reconstruct the history of the universe, from the formation of the first stars to the emergence of complex cosmic structures. The farther we look into space, the further back we are able to see into time. This is why studying high redshift galaxies is so crucial for understanding the origins of the universe. By observing galaxies that are billions of light years away, we are seeing them as they were billions of years ago, providing us with direct evidence of how the universe has evolved. Every redshifted galaxy we observe is like a snapshot of the universe at a moment in its distant past, offering us clues about the early stages of cosmic history, when the universe was much simpler and far less structured. This ability to study galaxies at such extreme distances offers an unparalleled opportunity to explore the cosmic past. The light we see from galaxies like Andromeda or other distant galaxies has traveled for millions, sometimes billions of years. As it reaches us, it brings with it a snapshot of what the universe looked like at that time, before the formation of the galaxies, stars, and structures we are familiar with today. In a sense, every distant galaxy is a time traveler, allowing us to witness the unfolding of the universe's earliest moments. The study of redshift and distant galaxies is an exciting and rapidly expanding field of research. With each new discovery, scientists gain more insight into the birth of galaxies, stars, and even black holes. Over the next few decades, we may unlock even more secrets, perhaps discovering signs of life from distant worlds, or even clues pointing to the existence of extraterrestrial civilizations. As we continue to explore the distant universe, we will expand our understanding of not only how the universe began, but also how it continues to evolve, possibly even opening doors to questions about time itself. In many ways, redshift is more than just a shift in the color of light. It is a gateway to understanding the distant past. When we study galaxies at high redshift, we are essentially looking back in time and witnessing the universe as it was when it was still young, and in the process of evolving into the cosmos we observe today. These galaxies preserve crucial information about the birth of stars, the formation of galaxies, and the ongoing transformation of the universe over billions of years. Through the study of redshift, we are able to experience a form of time travel, observing the earliest moments of the universe unfolding as if they were happening right now. This journey into the past is not only awe-inspiring, but also humbling, reminding us of how vast and ancient the universe truly is. As we continue to study these distant, high redshift galaxies, each new discovery brings us closer to answering some of the most profound questions about the origins of the universe, the nature of time, and the potential for life beyond Earth. Each new galaxy, each new piece of data is like a step further into the cosmic story, unraveling the mysteries of our universe one redshift at a time. The early galaxies of the universe, which first began to take shape after the Big Bang, were far simpler than the ones we observe today. These nascent structures were generally smaller, less complex, and predominantly consisted of young, glowing stars. Crucially, they were composed of a limited number of elements, with few heavy elements, such as carbon, oxygen, or iron, which are essential for the formation of complex structures. The lack of these heavier elements made these galaxies appear relatively simple and primitive compared to the intricate cosmic systems that would later evolve. Yet, despite their simplicity, these early galaxies played an essential role in laying the groundwork for the larger, more complex galaxies and clusters that would eventually emerge over billions of years. As the universe continued to expand following the Big Bang, these galaxies served as the building blocks for the sprawling cosmic structures that make up the universe today. The expansion of the universe, an event triggered by the Big Bang, continues unabated, with galaxies slowly but surely drifting further apart. This process, which has been ongoing for billions of years, is not only continuing, but actually accelerating, a mystery that has confounded scientists for years. As time progressed, the universe evolved. Galaxies collided, merged, and grew in size, undergoing complex processes that transformed them into the massive and intricate structures we observe in the cosmos today. However, in recent years, the scientific community has been stunned by revelations from the JAMES WEBB Space Telescope, JWST, which has made discoveries that challenge and expand our previous understanding of the universe's evolution. One of the most groundbreaking findings is the discovery of galaxies that formed much earlier than previously believed. For years, scientists theorized that the first galaxies in the universe emerged about 400 to 500 million years after the Big Bang. This assumption was based on the understanding that the universe needed time to cool down enough for stars to form from the remnants of the Big Bang, the vast clouds of gas and particles left behind after the initial explosion. However, the JWST has detected galaxies that appear to have emerged only a few hundred million years after the Big Bang, a much earlier formation than anyone anticipated. What's even more astonishing is the maturity of these galaxies. Rather than being primitive and chaotic, many of these newly discovered galaxies exhibit highly organized structures with well-formed stars and signs of active star formation. This suggests that these galaxies formed much faster than we previously thought possible. This discovery is shaking the foundations of cosmology, rewriting what we understand about the speed and mechanisms behind the formation of galaxies in the early universe. Among the most surprising discoveries made by the JWST is the detection of a galaxy that formed just 230 million years after the Big Bang. This finding is extraordinary because it challenges the long-held belief that galaxies took hundreds of millions of years to form. The fact that a galaxy could form so quickly after the Big Bang suggests that the conditions of the early universe were much more conducive to galaxy formation than we ever realized. It implies that the mechanisms governing the birth of galaxies, whether through the gathering of matter or the processes by which stars are born, may have been far more efficient than we once thought. These revelations are prompting new questions about the nature of the early universe. If galaxies could form so rapidly, what does that tell us about the conditions that existed in the first few 100 million years after the Big Bang? Could there have been unknown factors, such as unusual forms of dark matter or chemical processes that were previously overlooked, that allowed these galaxies to take shape so quickly? These new questions are challenging established models of the universe's origins, and they open up exciting possibilities for what might have really been happening during the universe's early days. The discovery of these ancient galaxies also reveals something unexpected: the high rate of star formation occurring within them. Scientists had long assumed that star formation in the early universe would be slow due to the scarcity of heavy elements. Elements like carbon and oxygen, which are essential for the formation of stars, are produced in the cores of older stars and then spread throughout space when those stars die. With the early universe being mostly devoid of these elements, it was believed that star formation would be a slow and gradual process. Yet the JWST's observations suggest otherwise. Many of these early galaxies appear to be bursting with new stars, challenging our previous assumptions about the rate of star formation in the nascent universe. This discovery could mean that the conditions for star formation were more favorable in the early universe than we thought. Alternatively, it might suggest that we misunderstood the process by which the first stars were formed. Perhaps the first stars did not require the heavy elements we thought they did, or maybe they were born in a completely different way than we had imagined. Whatever the case, this new information is forcing scientists to reconsider their models of how stars and galaxies came into being. Moreover, some of the galaxies discovered by the JWST are much larger and more complex than scientists had anticipated. These galaxies, which formed only a few 100 million years after the Big Bang, exhibit detailed structures and a variety of stars, defying the old notion that galaxies in the early universe were small, simple, and lacking in diversity. The discovery of such large and intricate galaxies so early in the universe's history calls into question the accuracy of our previous assumptions about the pace of galactic evolution. The findings of the JWST also have implications for our understanding of dark matter and dark energy. For decades, scientists have been trying to unravel the mysteries of these elusive substances, which account for the majority of the universe's mass and energy. While we still don't fully understand dark matter or dark energy, the new discoveries suggest that these forces may have played a much more significant role in shaping the universe than we previously realized. Perhaps dark matter had a more profound influence on the creation of galaxies, or dark energy might have contributed to the accelerated expansion of the universe in ways we are only beginning to comprehend. The more we learn about the universe, the more we realize how much remains hidden from us. These discoveries suggest that dark matter and dark energy may have shaped the universe's development in ways that are far more complex than we ever imagined. They may hold the key to understanding not only how galaxies formed, but also why the universe is expanding at an accelerating rate. The discoveries made by the James Webb Space Telescope could have profound implications for our understanding of the universe's early stages. It is becoming increasingly clear that many of our long-held ideas about the origins of galaxies and the universe as a whole are incomplete or even inaccurate. This means that scientists will need to develop new theories and models to explain the rapid formation of galaxies and the unusual conditions that allowed this to happen. It is an exciting time in scientific research as these groundbreaking discoveries open up the possibility of entirely new explanations for the formation of the universe. As scientists continue to study these ancient galaxies, they may uncover even more surprising facts about how galaxies and other cosmic structures evolved during the first few 100 million years after the Big Bang. This period, which remains one of the most mysterious and least understood chapters in the history of the cosmos, may be about to reveal secrets that will fundamentally change our understanding of the universe's origins. The new findings from the JWST are not just reshaping the past, They are paving the way for future discoveries that could alter the course of cosmology itself. The implications of these discoveries extend far beyond the formation of galaxies. They may also provide answers to some of the most profound mysteries about the universe, such as how galaxies interacted with each other in the earliest stages of cosmic history. These interactions could have been much more dynamic than we once thought, revealing a far more interconnected early universe than we previously believed. With each new revelation from the James Webb Space Telescope, we are coming closer to unlocking the deepest secrets of the universe, secrets that could illuminate not only the birth of galaxies, but also the very foundations of existence itself. The James Webb Space Telescope, JWST, has already begun to redefine our understanding of the universe. Its findings have given us a glimpse into a cosmic past that was once beyond our reach, unveiling some of the oldest galaxies known to humanity. These galaxies, which emerged far earlier and at a much faster pace than current models predicted, are fundamentally altering the theories surrounding the formation of the cosmos. As scientists sift through these unprecedented revelations, one thing becomes strikingly clear. The universe is much more complex and mysterious than we ever imagined. One of the most groundbreaking discoveries to emerge from the JWST is the identification of galaxies that are significantly older and larger than anything previously observed. This discovery challenges our long-standing assumptions about the pace at which galaxies formed in the early universe. Among these incredible finds is a galaxy known as GNZ11, which lies a staggering 13.4 billion light-years away. This means that by observing GNZ11, we're actually looking at the galaxy as it existed just 400 million years after the Big Bang, an era when the universe was still in its infancy. What makes GNZ11 so surprising is not only its sheer size, but also its rapid expansion. The galaxy is packed with hundreds of billions of stars, rivaling our own Milky Way, even though it is far younger. In fact, it's growing at an astonishing rate, far faster than scientists had ever predicted for such an early stage in cosmic history. The speed at which GNZ11 is expanding hints at an abundant supply of gas, vital fuel for star formation, available during a time when the universe was still forming. This discovery has forced astronomers to reconsider the models they have relied on to understand how galaxies evolve. The size and rapid growth of GNZ11 simply don't fit into the frameworks that have dominated our understanding of cosmic evolution. In addition to GNZ11, researchers have uncovered other early galaxies that defy expectations. These galaxies are not only massive, but they also exhibit complex structures, contain a high number of stars, and in some cases, harbor supermassive black holes at their centers. This is remarkable because we had once believed such massive and intricate galaxies wouldn't have emerged until much later in the universe's history. The fact that these galaxies existed so early forces us to question everything we thought we knew about how galaxies form and develop. The most puzzling aspect of these discoveries is how these ancient, massive, and well-structured galaxies come so quickly, considering the universe was still evolving during that period. The universe itself was in a phase of rapid expansion, and the conditions were vastly different from what we see today. How then could such complex structures emerge in such a short span of time? One plausible theory is a process called direct collapse. In this scenario, instead of galaxies gradually forming through the slow accumulation of stars and gas over millions of years, some ancient galaxies might have collapsed rapidly from enormous clouds of gas. This process could have allowed galaxies to form in a fraction of the time it would typically take. This theory offers an explanation for how such massive and organized galaxies could have existed so early in the universe's history. However, another potential explanation centers on the extreme conditions of the early universe. In the first few 100 million years after the Big Bang, the universe was a violent, chaotic place. Gas and radiation were abundant, creating an intense environment. This may have played a significant role in the accelerated formation of galaxies. The gas, driven by intense energy, might have been forced into dense pockets, eventually coalescing into the stars and structures that formed galaxies. Under such extreme conditions, galaxies could have grown much faster than previously believed. The energetic forces of the early universe likely catalyzed the rapid formation of these cosmic structures. Dark matter, a mysterious and invisible substance, may have also played a crucial role in the accelerated growth of these early galaxies. Dark matter doesn't emit light, but it exerts gravitational influence, shaping the behavior of stars and galaxies. It's possible that dark matter, concentrated in specific areas of the early universe, helped these ancient galaxies grow rapidly by pulling in additional gas and stars through its gravitational force. If this theory holds true, it would explain how some of the earliest galaxies grew so large, so quickly, in a time when the universe was still in its formative stages. Perhaps one of the most fascinating aspects of these ancient galaxies is the presence of supermassive black holes at their centers. These black holes are not just larger than any we've seen in our own galaxy. They are truly enormous, containing millions or even billions of times the mass of our sun. Typically, black holes of such immense size are thought to form over the course of billions of years, as massive stars collapse under their own gravity. However, the black holes found in these ancient galaxies seem to have formed much more rapidly than expected. This raises a series of questions about the processes that could have allowed such massive black holes to grow so quickly, especially when we consider that they should have taken much longer to develop. One possible explanation for the rapid formation of these supermassive black holes is direct collapse, a process in which a massive cloud of gas, much larger than anything we observe today, collapses directly into a black hole. In the extreme conditions of the early universe, such a collapse could have created these colossal black holes in far less time than traditional models predict. This theory not only challenges our understanding of black hole formation, but also sheds light on the unique conditions that allowed the universe to evolve in the way that it did. As the JWST continues its mission to uncover the hidden wonders of space, it opens the door to a new era of cosmic discovery. With each new revelation, our understanding of the universe deepens, and our conception of its origin and evolution becomes ever more complex. We are standing on the edge of a new frontier in our exploration of the cosmos, one where the very fabric of space-time is beginning to reveal secrets that were once unimaginable. These discoveries are not just changing the way we view the universe, they are rewriting the story of our existence within it. And as the search for answers continues, one thing remains certain. The universe is far more mysterious, far more intricate, and far more astonishing than we could have ever conceived. The journey to uncover its full story is only just beginning. In the early universe, the process of galaxy formation was far more chaotic and unpredictable than astronomers once imagined. Galaxies, instead of slowly coalescing over billions of years into the orderly spiral and elliptical forms we are familiar with today, formed in a much more turbulent manner. Some galaxies might have even skipped the usual stages of evolution, bypassing the formation of stars altogether and collapsing directly into black holes. This rapid collapse, devoid of the usual stellar life cycle, could explain why certain black holes appeared much larger than expected so soon after the universe's creation. In fact, these massive black holes seem to have emerged far too early, challenging our previous understanding of how they should have developed. Normally, stars first form from clouds of gas and dust. Over time, these stars might go through a life cycle that eventually leads to the formation of black holes. However, the theory that some black holes could have formed in a more direct and catastrophic way, skipping those earlier stages, might help explain the immense size of black holes observed in the very early universe. These black holes could have grown rapidly by consuming enormous amounts of gas from the surrounding galaxies, accumulating mass at a remarkable speed. This feeding frenzy could have accelerated their growth, allowing them to become giants much faster than expected. As a result, we now have to rethink how black holes formed and evolved in the first few billion years after the Big Bang. This theory also has wider implications for the formation of galaxies themselves. Astronomers had long believed that galaxies evolved gradually, with stars slowly clustering together through the gravitational pull of the matter that constituted them. But these discoveries have forced scientists to revise their previous assumptions. It seems that some galaxies didn't take billions of years to form. Rather, They assembled much more rapidly than anyone thought possible. This realization has prompted fresh speculation about how galaxies came into being and how diverse the processes of galaxy formation might have been across different regions of the universe. Some galaxies could have formed through quick, explosive processes, while others took their time. The early universe might have seen a mixture of these contrasting scenarios, with rapid and slow galaxy formation coexisting in different pockets of space. As scientists continue to explore these new possibilities, they are also rethinking the role of dark matter in galaxy formation. Dark matter, which remains largely mysterious to us, makes up a significant portion of the universe's mass. It doesn't emit light or energy, but its gravitational influence is undeniable. Without dark matter, galaxies wouldn't have enough mass to hold themselves together. It is believed that dark matter might have played an even greater role in the formation of galaxies than previously thought. In the early universe, dark matter wasn't distributed evenly. Instead, it formed dense clumps that acted like cosmic magnets, pulling in vast clouds of gas and dust. These clumps of dark matter helped create the gravitational conditions necessary for the birth of stars and eventually entire galaxies. However, because dark matter was clumped unevenly, galaxies that formed around these pockets of dark matter were not the neatly structured spirals we see today. Instead, they were often twisted, irregular, and chaotic. This chaotic formation process reflected the universe's overall turbulence during its early years, when galaxies were still colliding, merging, and evolving into the more familiar shapes we recognize today. These collisions didn't involve stars themselves crashing into one another. Stars are so far apart that they rarely collide. But the gas and dust between the stars were much more densely packed and prone to interactions. When galaxies merged, these clouds of gas and dust collided, compressed, and heated up, often triggering the birth of new stars. These violent interactions could reshape entire galaxies, leading to the formation of larger and more structured systems over time. This process of galaxy mergers played a crucial role in shaping the universe we see now. In the early universe, galaxies were much smaller and much closer together, so they collided far more frequently. Today, these types of cosmic smash-ups still occur, but the galaxies are more widely spaced. In the past, however, the high density of galaxies in certain regions of space made collisions more common and more intense, significantly influencing the overall structure of the universe. In addition to the more chaotic process of galaxy formation, the composition of these early galaxies was very different from the galaxies we observe today. Early galaxies contained a much higher amount of gas, primarily hydrogen and helium. This gas, the building blocks of stars, was much more abundant in the early universe, and because of this, galaxies were more chaotic. The gas didn't always settle into neat, organized shapes. Rather, it was often distributed unevenly, resulting in galaxies that appeared disordered and irregular. The stars themselves formed at a different rate and in different patterns than we see today. The high density of gas in these galaxies created conditions for rapid star formation, but the chaotic nature of these early galaxies meant that their structure was anything but orderly. The chaotic, irregular appearance of these galaxies has caused astronomers to reconsider their previous ideas about galaxy formation. They had once believed that as galaxies aged, they would become more structured, more orderly. But the first galaxies didn't follow this trajectory. Instead of developing into neat spirals or smooth ellipses, they remained in a state of turbulence, continually evolving, merging, and growing. But how do we know what these early galaxies looked like? Given that they are so far away and the universe is so vast and ancient, how can we possibly observe them? The answer lies in the nature of light itself. Light doesn't travel instantly, it takes time to reach us. When we observe distant galaxies, we are looking at light that has traveled across space for billions of years. The farther away a galaxy is, the longer it takes for its light to reach us. And thus, when we observe these distant galaxies, we are seeing them as they appeared long ago in the very early stages of the universe. To peer into this distant past, astronomers use powerful telescopes, such as the Hubble Space Telescope and the JAMES Webb Space Telescope. These tools allow us to capture images of galaxies that are billions of light years away, offering a glimpse into what the universe looked like in its infancy. Through these telescopes, we can observe galaxies in their early stages of formation, unraveling the complex processes that led to the creation of the universe's vast structures. One of the most important tools in this exploration is the James Webb Space Telescope, which was specifically designed to study the distant and ancient objects of the universe. Its ability to detect infrared light, which is crucial for observing galaxies whose light has been stretched into longer wavelengths by the vast distances it travels, provides a much clearer picture of the earliest galaxies. What these images reveal is surprising. Far from the orderly, structured galaxies we see today, many of the galaxies observed by the James Webb Space Telescope appear to be irregular, chaotic, and far more disorganized than astronomers had expected. This has led scientists to rethink their previous ideas about how galaxies formed and evolved. Instead of a smooth and steady per-galaxy formation, may have been a far more explosive and turbulent process than we had realized. One of the explanations for this chaotic appearance involves dark matter. Dark matter, an invisible substance that makes up a significant portion of the universe's mass, played a key role in shaping the early universe. Although we can't directly observe dark matter, we know it's there because of its gravitational effects on visible matter. In the early universe, dark matter wasn't spread out evenly. Instead, it formed dense clumps in certain regions of space, which helped pull in gas and dust, creating the conditions necessary for galaxies to form. These clumps of dark matter acted as the gravitational anchors around which galaxies formed, but because dark matter was unevenly distributed, the resulting galaxies were not the smooth, symmetrical systems we see today. Instead, they were twisted and irregular, a reflection of the turbulent and chaotic conditions of the early universe. As time passed and galaxies continued to merge and evolve, they slowly began to take on the more structured forms we recognize today. However, the legacy of their chaotic beginnings can still be seen in the irregularities of some ancient galaxies. These discoveries continue to challenge our understanding of the universe's early days, offering new insights into the processes that shape the cosmos and providing us with a more complex and dynamic picture of the universe's evolution. In the vast expanse of modern galaxies, star formation is a highly controlled and concentrated process. Stars are born primarily in specific regions, such as the spiral arms of galaxies like our own Milky Way. This is a far cry from the early universe, where the process of star formation was far more chaotic, rapid, and unpredictable. In those formative days, stars could form nearly anywhere within a galaxy, often in bursts triggered by the turbulence of the cosmos or the violent merging of galaxies. This lack of regulation and organization gave early galaxies a distinctive, irregular, and sometimes clumpy appearance. The reason for these chaotic formations lies in the fact that galaxies during the early universe were still evolving. Unlike today, when galaxies are more mature and stable, the early galaxies were still in the process of shaping themselves. Over time, as galaxies collided and merged, they began to settle into more defined structures. The chaos that once marked their formation gave way to more organized systems, allowing the distinct shapes we recognize today, such as spiral arms or elliptical bodies, to emerge. But while the stars in modern galaxies are primarily born in these well-defined regions, understanding the early universe offers astronomers crucial insights into how galaxies evolved and how the magnificent, organized galaxies of today came to be. At the very heart of most large galaxies lies a supermassive black hole, a powerful, enigmatic object so dense that its gravitational pull is so strong that not even light can escape once it gets too close. These black holes, however, are not passive structures. On the contrary, they play an active and profound role in shaping their surrounding galaxies. It is believed that in the early universe, long before galaxies had fully taken shape, supermassive black holes were already beginning to form at the centers of young galaxies. The immense gravitational forces exerted by these behemoths likely attracted vast clouds of gas, dust, and even entire stars, helping to shape the evolution of these young galaxies. In some instances, the gravitational pull of these black holes could have caused galaxies to become highly turbulent and disordered, disrupting the otherwise peaceful movement of stars and gas and preventing the galaxies from settling into more regular shapes. Yet, black holes do not merely draw things in. They are capable of releasing incredible amounts of energy when matter spirals towards them. As gas and other material fall toward the black hole, they heat up to extreme temperatures, emitting intense radiation. In some cases, black holes also generate powerful jets of high-energy particles, shooting them out at nearly the speed of light. These jets can have profound effects on their surrounding environment, blasting through space and potentially reshaping the galaxy. These outbursts could have disrupted the formation of new stars, scattered gas and dust, and contributed to the chaotic, irregular appearance of early galaxies. Even today, scientists continue to probe the exact role these supermassive black holes played in the evolution of the universe. But one thing is certain: they were far from passive observers. They actively shaped the very structure of the cosmos. As the universe continued to age, galaxies began to adopt more recognizable forms. Shortly after the Big Bang, the universe was a tumultuous, unstable place, filled with swirling clouds of gas, dust, and newly forming stars. The first galaxies that emerged were often irregular and unpredictable in shape, clumps of stars and matter scattered throughout space. However, over billions of years, the invisible force of gravity began to assert its dominance. Galaxies interacted, collided, and sometimes merged, and these cosmic events often led to remarkable transformations. During these collisions, the stars within the galaxies did not directly crash into one another, as the distances between them were vast. Instead, the gravitational forces at play stirred up vast clouds of gas and dust, triggering new waves of star formation. Over time, this process led to more structured galaxies, with the spiral arms of galaxies like the Milky Way or the rounded, smooth shapes of elliptical galaxies taking shape. Yet even today, galaxies continue to grow and change. They merge, interact, and reshape one another in an ongoing cosmic dance. Our very own Milky Way, for example, is on a collision course with the nearby Andromeda galaxy. This dramatic event will unfold over the next few billion years, ultimately leading to the formation of a new, larger galaxy. This ongoing transformation shows that the process of galaxy formation and evolution is far from finished. One of the most groundbreaking discoveries in modern astronomy has been the realization that early galaxies were far more chaotic than scientists once thought. This new understanding challenges previous ideas about how galaxies form and suggests that the process is far more complex and unpredictable than originally imagined. The unusual, irregular shapes of these early galaxies offer important clues about the nascent universe, revealing a time when the cosmos was still forming, still chaotic, and still uncertain. The exact forces and conditions that shape these early galaxies remain a mystery, and unraveling this enigma continues to challenge researchers. But as astronomers continue to study these ancient, disordered galaxies, they are piecing together a clearer picture of how galaxies come into being, how they evolve, and how they ultimately grow into the complex and structured systems we observe today. The study of these ancient galaxies is shedding light not only on the distant past, but also on the powerful forces that shape the cosmos as a whole. The strange, irregular forms of the first galaxies are like the universe's fingerprints, offering invaluable insight into how galaxies form, collide, and transform over time. As technology continues to advance, astronomers are peering deeper into space, seeking to unlock even more mysteries about the early universe. What we know now is only the beginning, and with each new discovery, we edge closer to understanding the true nature of the universe and the cosmic forces that have shaped it. One of the most thrilling breakthroughs in modern astronomy is the detection of the earliest light that originates from galaxies formed just 200 to 300 million years after the Big Bang. This light offers an extraordinary window into the universe's earliest days. During this time, the universe was filled with a thick fog of particles that trapped photons, preventing light from traveling freely. These particles interacted with photons, scattering them in all directions and effectively creating a dense, impenetrable fog. It took hundreds of thousands of years for the universe to cool down and expand enough to allow light to break free. This moment, when photons could finally escape, marks what we call the cosmic microwave background, CMB, a faint glow that provides the oldest observable light from the early universe. The light we observe today from the first galaxies, which formed 200 to 300 million years after the Big Bang, is truly remarkable. It represents one of the earliest sources of starlight to ever be emitted in the history of the universe. This light is not just a faint, distant signal. It's the result of the birth of the very first galaxies and stars. It represents a pivotal moment in cosmic history, when the universe transitioned from a dark, dense fog into a brilliant expanse of light, stars, and galaxies. This event, often referred to as the cosmic dawn, marks the beginning of a new era in the evolution of the universe, laying the foundation for the cosmic landscape we observe today. The significance of this discovery is immense. For the first time, scientists have uncovered light that has traveled billions of years to reach us. This light holds the secrets to understanding the cosmic dawn, the moment when the universe began to emerge from its chaotic, hot, and dense post-Big Bang state. The birth of the first galaxies and stars cleared the fog of particles that had once obscured light, allowing the cosmos to shine brightly for the first time. This pivotal moment marks the transition from the primordial darkness to the sparkling, star-filled sky we see today. The discovery of this earliest light provides us with a glimpse into a time long before our solar system or even our galaxy came into existence. This era, known as the cosmic dawn, is key to understanding how the universe evolved from its incredibly hot, dense early state into the vast, diverse cosmos we observe today. For years, scientists had suspected that galaxies formed during this period, but proving this theory was an immense challenge. The primary difficulty lay in the vast distances separating us from these distant galaxies. The farther away an object is, the longer its light takes to reach us. As such, the light from galaxies formed billions of years ago is incredibly faint by the time it reaches Earth. Nonetheless, the ability to observe this light has revolutionized our understanding of the early universe, offering a glimpse into the moments that ultimately led to the formation of our own galaxy and everything that followed. The light we observe today from distant galaxies carries with it a story of the universe's earliest moments, an extraordinary glimpse into the beginning of everything we know. However, to fully appreciate the magnitude of this discovery, it is crucial to understand the transformation that light has undergone on its long journey through the cosmos. As the universe has been expanding ever since the Big Bang, the wavelengths of light traveling through space have also been stretched, moving beyond the visible spectrum and into the infrared range. This shift, known as redshift, renders the light invisible to the human eye. As a result, specialized technology, particularly powerful telescopes, is required to detect and study this faint, stretched light from the farthest reaches of space. Without such advanced instruments, the study of these distant galaxies, some of the first to form after the Big Bang, would be nearly impossible. These galaxies emit light that originated billions of years ago, and in order to observe it, scientists need telescopes capable of detecting infrared radiation, a form of light that is invisible to us. This requirement marks a significant challenge in understanding the very first light of the universe, but it also presents an incredible opportunity. By utilizing state-of-the-art telescopes like NASA's JAMES WEBB Space Telescope and the Hubble Space Telescope, as well as powerful ground-based observatories, we are now able to capture signals that have traveled across the cosmos for billions of years. These instruments allow us to peer back in time, helping us unlock the secrets of the universe's earliest stages, mere moments after the Big Bang. One of the most remarkable aspects of this discovery is the collaboration between space-based and ground-based observatories. The combination of these tools has proved essential in revealing this ancient light, giving us a clearer understanding of how the universe began and evolved. Through this collaboration, scientists have been able to peer deeper into the fabric of space than ever before, detecting faint signals that trace their origins to the very birth of galaxies and stars. A fundamental challenge in detecting this ancient light lies in the fact that the universe has been expanding ever since the Big Bang. As space stretches, so does the light traveling through it. This stretching process causes the wavelength of light to increase, shifting it from the ultraviolet and visible spectrum to the infrared. By the time this light reaches us, it no longer remains in the visible range, but instead falls into the infrared spectrum, which requires infrared detecting telescopes to observe. The James Webb Space Telescope is specifically designed to capture this infrared light, providing us with an unprecedented view into the depths of the universe. This specialized ability enables Webb to observe objects that are beyond the reach of traditional telescopes, opening up new avenues for discovery. The light we can now see from galaxies that formed just 200 to 300 million years after the Big Bang offers a wealth of information about the universe's infancy. These galaxies were among the first to form, and their light provides crucial insights into the early stages of cosmic evolution. Scientists have long wondered how quickly the universe began to form organized structures, such as galaxies, after its explosive start. The discovery of these distant galaxies challenges our previous assumptions, showing that the universe began to organize itself much sooner than we had anticipated. The first galaxies to emerge were very different from the ones we observe today. They were smaller, irregular, and far more chaotic in structure. Over time, these tiny galaxies merged and collided, eventually growing into the massive, well-structured galaxies that dominate the universe now. By examining the characteristics of these early galaxies, scientists are piecing together the history of galaxy formation, shedding light on the processes that led to the universe we see today. Moreover, these early galaxies help us understand the role of the first stars, known as population 3 stars, in shaping the universe. These stars, formed from the simplest elements, hydrogen and helium, were vastly different from the stars we are familiar with today. They were hotter, brighter, and more massive than modern stars, burning through their fuel at an astonishing rate. Their short lives and intense energy output played a crucial role in the evolution of the universe, producing the first heavy elements and triggering the process of cosmic reionization. This process transformed the neutral hydrogen gas that filled the early universe into ionized particles, allowing light to travel freely across the cosmos for the first time. The energy released by these stars helped illuminate the universe, paving the way for the formation of galaxies, stars, and ultimately the cosmos as we know it. This ancient light also provides us with a unique opportunity to study some of the most mysterious and elusive forces in the universe, dark matter and dark energy. Despite making up the majority of the universe's mass and energy, these forces remain invisible and largely undetectable. Dark matter, for example, doesn't interact with light, making it difficult to observe directly. However, its gravitational pull affects the formation and movement of galaxies, and by studying the way galaxies formed in the early universe, scientists can infer the influence of dark matter on their development. Similarly, dark energy, which is believed to be responsible for the accelerating expansion of the universe, remains one of the greatest mysteries in modern physics. By examining the light emitted by early galaxies, scientists hope to gain deeper insights into how dark energy and dark influenced the universe's evolution. This ancient light offers a unique window into the forces that have shaped the universe from its earliest days. Looking ahead, scientists are poised to make even more groundbreaking discoveries as new, more powerful telescopes are developed. The discovery of light from galaxies formed only 200 to 300 million years after the Big Bang is just the beginning. With advancements in technology, such as the continued development of the James Webb Space Telescope, we are on the verge of uncovering even more secrets about the universe's origins. Each new discovery takes us one step closer to answering some of the most profound questions about the cosmos, including how galaxies formed, how the first stars ignited, and how the universe has evolved into the complex structure we observe today. In addition to unraveling the mysteries of galaxy formation and stellar evolution, this study of ancient light also opens up new possibilities for understanding time and space itself. The light we are now observing began its journey millions, even billions of years ago, and in a very real sense, we are looking back in time. Through this ancient light, we can witness events that happened long before Earth or even our solar system existed. It is as if we are peering into a distant past when the universe was radically different from what we know today. Furthermore, the discovery of primordial black holes hypothetical objects formed just moments after the Big Bang, adds another layer of intrigue to the story of the universe's birth. Unlike the black holes we are familiar with, which form from the collapse of massive stars, primordial black holes are thought to have emerged from the extreme conditions of the early universe itself. These black holes could have formed when dense regions of space collapsed under their own gravity, creating objects that may still exist today, making them some of the oldest objects in the universe. Their presence could provide critical insights into the early universe's structure and the forces that governed its evolution. As we continue to study this ancient light, we are not only uncovering the history of galaxies and stars, but also gaining a deeper understanding of the fundamental forces that govern the universe. This journey into the past holds the promise of answering some of the most profound questions in science, questions that stretch to the very fabric of time and space. With each new discovery, we are one step closer to unraveling the mysteries of the cosmos, revealing the interconnectedness of all things, and exploring our own place in this vast and ever-expanding universe. The study of ancient light from the first galaxies and stars is one of the most exciting and important fields of modern astronomy. With each new observation, scientists are opening new windows into the past, allowing us to peer back to the very beginning of the universe and gain a deeper understanding of how everything came to be. As our technology continues to advance, there is no telling what new discoveries lie ahead, but one thing is certain: the journey to uncover the secrets of the universe's early days has only just begun. In the early universe, shortly after the Big Bang, the cosmos was a seething cauldron of intense heat, energy, and dense particles. In this chaotic environment, regions of space were not evenly distributed. There were slight fluctuations in the density of matter. Most of these irregularities smoothed out over time as the universe expanded, but some areas became so dense that gravity pulled them inward, leading to the formation of an entirely different type of black hole: primordial black holes. These primordial black holes would have formed in the very first moments after the Big Bang, during an era when the universe was a hot, turbulent, and dense place. In this early universe, gravity was extraordinarily powerful, and the density of matter was so high that tiny regions could collapse into incredibly compact, minuscule black holes. These early black holes weren't the supermassive giants we observe today at the centers of galaxies. Rather, they were small, possibly as tiny as an atom, yet packed with a remarkable amount of mass. Despite their size, they had the potential to be just as potent, or even more so, than the massive black holes that would later form from dying stars. What makes these primordial black holes particularly intriguing is the possibility that they could explain some of the greatest mysteries of the universe, such as dark matter. Dark matter, which is believed to make up most of the mass of the universe, is invisible to our telescopes. It doesn't emit, reflect, or absorb light, which makes it nearly impossible to detect directly. Yet its gravitational influence on visible matter is undeniable. Some scientists speculate that primordial black holes, which formed under the extreme conditions of the early universe, could be responsible for dark matter, or at least a portion of it. While the idea of primordial black holes might sound like a fantastical theory, it is grounded in the laws of physics and cosmology. These black holes are not thought to have formed from the collapse of stars, like the stellar black holes we are familiar with today. Instead, primordial black holes could have appeared spontaneously, forged from fluctuations in the density of matter during the universe's earliest moments. The fact that these objects could have formed without the need for a star to collapse makes them fundamentally different from the black holes we see in the present day. Given the conditions of the young universe, primordial black holes might have varied greatly in size. Some could have been incredibly small, perhaps no larger than a proton, while others might have been as large as asteroids or even a fraction of the mass of Earth. What's more, these black holes would have been incredibly dense, packing an immense amount of mass into their tiny volumes. This density would make them behave in fascinating and unusual ways, different from the black holes that form from the collapse of massive stars. And it's possible that they could even help explain some of the deepest mysteries of the cosmos. The potential connection between primordial black holes and dark matter is one of the most compelling aspects of this theory. Dark matter is theorized to make up about 85% of the universe's total mass, yet it remains invisible to traditional observational techniques. It exerts its influence only through its gravitational effects on galaxies, galaxy clusters, and even the cosmic web itself. If primordial black holes do exist, they might be a key component of this invisible mass. Their gravitational pull could explain why galaxies rotate at the speeds they do, and why galaxies appear to have more mass than is visible in the form of stars, gas, and dust. Despite the fact that primordial black holes are a captivating theoretical concept, there is still no direct evidence for their existence. Researchers have been exploring a number of ways to uncover these elusive objects, and some intriguing clues have already emerged. One of the most promising ways to detect primordial black holes is through the study of gravitational waves. These ripples in space-time, first predicted by Albert Einstein, are generated when massive objects such as black holes collide. In recent years, scientists have detected gravitational waves from events that could potentially involve the merging of primordial black holes. If this trend continues, it might provide strong evidence that these ancient objects are real and that they are hidden throughout the universe. Another avenue of investigation is the study of the cosmic microwave background, CMB, radiation. This faint afterglow of the Big Bang still lingers in space, offering a snapshot of the universe's early conditions. By analyzing the subtle patterns in the CMB, scientists hope to uncover clues about the universe's infancy. If primordial black holes formed during the Big Bang, they could have left an imprint on this ancient radiation. Any disturbances or irregularities in the CMB caused by primordial black holes could serve as a crucial signature, one that might be detectable with advanced telescopes and space instruments. The notion that primordial black holes could account for dark matter is tantalizing. These objects, though invisible to direct observation, could exert enough gravitational influence to account for the phenomena we observe in galaxies and clusters of galaxies. For instance, dark matter appears to be responsible for the way galaxies rotate. Without the additional mass provided by dark matter, the outer stars and galaxies would be moving too quickly to be bound by the galaxy's gravity. Primordial black holes, with their immense gravitational pull, could be the elusive candidates for this missing mass. Moreover, primordial black holes could offer valuable insights into the very birth of the universe itself. Unlike the black holes we know today, which are formed from the collapse of dying stars, these ancient black holes would have emerged from the extreme conditions that prevailed only moments after the Big Bang. They could provide a window into the forces and dynamics that shape the cosmos, shedding light on the processes that led to the creation of stars, galaxies, and everything we see in the universe today. As scientists continue to study the properties of primordial black holes, they are confronted with the fascinating possibility that these objects could hold the key to understanding not just dark matter, but also the very nature of gravity, space, and time. If they exist, these primordial relics of the early universe might be scattered throughout space, hidden from view, but still exerting their gravitational influence on their surroundings. They may be invisible, but their existence could unlock secrets that have eluded researchers for centuries. Studying primordial black holes might be one of the most profound endeavors in modern cosmology. These objects, born in the first moments of the universe, could carry with them the answers to questions about the origins of the cosmos, the nature of dark matter, and the fundamental forces that govern space and time. If scientists can prove their existence, it would mark one of the most significant breakthroughs in our understanding of the universe, a discovery that could forever alter the way we view the cosmos and our place within it. From the planets that revolve around stars to the distant galaxies that stretch across the cosmos, the universe is filled with secrets waiting to be unraveled. One of the most captivating mysteries lies not in the matter we can see, but in the invisible forces that govern the cosmos. These invisible forces are tied to a concept that has puzzled scientists for decades: dark matter. Dark matter, despite comprising the majority of the universe's mass, remains undetectable by any known instruments, only revealing itself through its gravitational effects on visible matter. Yet there's an intriguing theory that could change everything we know about dark matter. Some scientists speculate that primordial black holes, mysterious and ancient objects formed in the very first moments after the Big Bang, could be the missing link in understanding dark matter. These primordial black holes might not only be key to unlocking the mystery of dark matter, but could also reshape our understanding of the universe itself. If these black holes do, in fact, contribute to the presence of dark matter, it would not just add a piece to the puzzle of the cosmos. It could rewrite the rules of astrophysics and cosmology as we know them. Primordial black holes, if they exist, could potentially reveal hidden laws of the universe, laws that challenge everything we currently understand. They could unlock the secrets of gravity, quantum mechanics, and even the very fabric of space and time itself. By studying these enigmatic objects, scientists hope to bridge the gap between Einstein's theory of general relativity, which describes how massive objects warp space-time, and quantum physics, which governs the behavior of particles on the smallest scales. If we could reconcile these two pillars of modern physics, we might come one step closer to discovering a unified theory of everything, an all-encompassing framework that explains the workings of the entire universe. However, despite the vast potential of primordial black holes, direct proof of their existence remains elusive. The clues we have gathered so far suggest they could be the missing piece in the puzzle of the universe's origins, but much more research is needed. These ancient black holes are thought to have formed during the earliest moments of the Big Bang, possibly holding vital information about the birth of galaxies, the elusive nature of dark matter, and the invisible forces that shape the cosmos. As advancements in telescopes, satellites, and scientific methods continue, researchers are hopeful that they will uncover more evidence to determine whether primordial black holes are real, and if so, what role they played in the formation of the universe. The universe is vast beyond comprehension, and with each discovery, we realize just how little we understand. Among its many mysteries are primordial black holes, ancient and invisible objects that might have formed at the dawn of time. These cosmic enigmas are not merely fascinating in their own right, they could hold the key to understanding the very origins of the universe itself. Scientists are particularly eager to study them, not only because they could shed light on how the universe began, but also because they could reveal new aspects of physics that we've never before imagined. This quest to understand primordial black holes represents one of the most exciting frontiers in modern science. When we peer into the vast expanse of space, using the most powerful telescopes available, we're not simply looking at distant objects. We're actually looking back in time. This may sound like science fiction, but it's the fascinating reality of how light works. Light doesn't travel instantaneously. It moves at a fixed speed, about 186,000 miles per second. While that may seem incredibly fast, the vastness of space means that light from the most distant galaxies takes millions, even billions of years to reach us. When we observe these faraway galaxies, we're seeing them not as they are today, but as they were billions of years ago, sometimes during an era when the universe was still in its infancy. It's in these ancient galaxies that astronomers have made a discovery that challenges the very foundation of our understanding of the universe. Some of these galaxies host supermassive black holes, gigantic objects with gravitational pulls so immense that not even light can escape. The shocking revelation is that these supermassive black holes appear to have formed much earlier in the universe's history than current scientific models suggest is possible. According to established theories, black holes form from the collapse of massive stars and gradually grow over billions of years by pulling in gas, dust, and even entire stars. However, these early supermassive black holes seem to have reached enormous sizes far faster than traditional models allow, raising profound questions about the very nature of black hole formation. The typical formation process for a black hole is gradual. It begins with a massive star that exhausts its fuel, eventually collapsing under its own gravity to form a stellar mass black hole. From there, the black hole begins to consume everything in its vicinity, growing larger and larger over time. This process is believed to take billions of years, and only after such a long accumulation of matter does the black hole become supermassive. But the supermassive black holes found in ancient galaxies seem to have formed much more quickly, bypassing the slow and gradual growth phase entirely. Some of these black holes existed less than 1 billion years after the Big Bang, a time when the universe itself was still in its infancy. This discovery raises a critical question. How could these black holes have grown so large so quickly? One possibility is that they formed through a special process in the early universe that allowed them to gain mass at an extraordinary rate. Some researchers suggest that the first black holes may have formed from enormous clouds of gas that collapsed directly into black holes, skipping the traditional star formation phase altogether. Another theory proposes the existence of primordial black holes, which could have formed in the very earliest moments of the universe, potentially explaining the rapid growth of these early supermassive black holes. To understand the true nature of these ancient black holes, it's essential to first grasp what a supermassive black hole actually is. At its core, a black hole is a region in space where gravity is so intense that not even light can escape its grasp. Once something crosses the boundary known as the event horizon, it's forever trapped. Black holes come in various sizes, from small stellar mass black holes to the truly enormous supermassive black holes, which can be millions or even billions of times more massive than our sun. Supermassive black holes are typically found at the centers of galaxies, including our own Milky Way, and they play an essential role in shaping the dynamics of their galaxies. Their immense gravity influences the movement of stars, the formation of new stars, and even the behavior of entire galaxies. In the Milky Way, the supermassive black hole Sagittarius A Sti sits at the galaxy's core. While it remains invisible to the naked eye, astronomers can observe its influence on nearby stars, which orbit around it at incredible speeds. Despite their name, black holes are far from empty voids. Instead, they are dynamic, powerful cosmic entities that have been shaping the evolution of galaxies for billions of years. In fact, some scientists believe that without supermassive black holes, galaxies as we know them might not even exist. Supermassive black holes don't simply appear overnight. Their growth is a slow and gradual process that begins with smaller stellar mass black holes. These smaller black holes form when massive stars reach the end of their life cycles and explode in a supernova. After the explosion, the remaining core collapses, forming a black hole. Over billions of years, these black holes can grow by accreting matter and merging with other black holes, eventually becoming the supermassive black holes that sit at the centers of galaxies. However, as surprising as it may sound, some supermassive black holes appear to have already reached their enormous sizes less than 1 billion years after the Big Bang. This presents a paradox because, according to current models of black hole formation, such rapid growth should be impossible. How could these early black holes have grown so quickly when the universe was still young and the material needed for their growth was sparse? It's as though we've discovered a fully grown tree in a place where the seed was only planted moments ago. This discovery challenges everything we thought we knew about black hole formation and growth. If these black holes can grow this quickly, then either they are gaining mass in ways we don't yet understand, or there is something missing in our current understanding of how the early universe evolved. Theories abound, from the suggestion that massive clouds of gas may have collapsed directly into black holes, to the possibility that primordial black holes formed in the first moments after the Big Bang. However, none of these theories have been proven, yet. The discovery of these ancient supermassive black holes is still one of the most perplexing puzzles in modern science, and it may hold the key to unlocking new and unexpected laws of physics that could change our understanding of the cosmos forever. Black holes, those enigmatic behemoths of the cosmos, are born from the collapse of massive stars, but their growth is a more complex story. Typically, black holes expand by drawing in gas, dust, and other matter from the space around them. However, their ability to do so isn't infinite. There's a crucial limit to their growth, known as the Eddington limit. This limit hinges on a delicate balance between two powerful forces: the gravity of the black hole pulling in matter, and the radiation pressure from the matter being pulled in. As a black hole swallows more and more material, it begins to emit intense radiation. This radiation creates an outward pressure that counteracts the inward pull of gravity. Once this radiation pressure becomes too strong, it effectively halts the black hole's ability to pull in more material at the same rapid rate. This natural boundary has long been believed to prevent black holes from growing too quickly. But recent theories have begun to challenge this traditional understanding. Some scientists suggest that under extreme conditions, black holes may have been able to break through the Eddington limit. These conditions, they argue, could have existed in the very early universe, when the forces at play were vastly different from what we observe today. Under these rare and special circumstances, black holes could have grown at a pace far beyond what we thought possible, accumulating mass much faster than we ever imagined and becoming far more massive than we previously thought was achievable. One particularly captivating theory posits that these supermassive black holes could have originated from primordial black holes, which may have formed shortly after the Big Bang. Imagine the universe. Just moments after the Big Bang, a chaotic and violent expanse of energy and matter, where gravitational forces were intense. In this early universe, the very first black holes may have already been massive, their growth igniting immediately. Because these primordial black holes started life already large, they had an immediate advantage in their ability to grow quickly. They could have become the supermassive black holes we see at the centers of galaxies today, with a kind of head start that allowed them to outpace the usual growth process. There's another intriguing theory that suggests black holes could have grown in groups rather than forming alone. These small black holes would have appeared in clusters, forming in the dense regions of the early universe. As they drifted toward one another, their gravitational attraction would have pulled them into close proximity, causing them to merge. This merging process would result in an exponential increase in size, and in a relatively short amount of time, these black holes could have grown to enormous sizes, possibly even becoming supermassive black holes. What's even more mind-boggling is the possibility that these supermassive black holes from the early universe could be offering clues to a much larger mystery, one that might hold the key to our understanding of the very fabric of the cosmos. Could these ancient black holes be signaling the presence of unknown forces, or even entirely new forms of matter that we have yet to discover? Some researchers believe that solving this mystery might lead to revolutionary breakthroughs in physics, potentially rewriting the laws that have guided our understanding of the universe for centuries. The search for answers is far from over. One of the most powerful tools in this quest is the JAMES WEBB Space Telescope, JWST. This remarkable instrument, which is already capturing extraordinary images of some of the universe's oldest galaxies, is allowing scientists to peer deeper into space than ever before. By studying these ancient galaxies and the supermassive black holes at their centers, astronomers hope to uncover how these colossal structures were able to form so early in the universe's history. Each new image captured by the JWST offers a tantalizing glimpse into the past, potentially bringing us one step closer to solving this cosmic puzzle. The discovery of these early supermassive black holes challenges everything we thought we knew about black hole formation. The fact that such massive black holes exist so soon after the Big Bang presents one of the most perplexing and exciting questions in modern astrophysics. But while we search for answers to these mysteries, another unsolved riddle continues to captivate scientists. Dark matter. Dark matter is an invisible, elusive substance that is thought to hold the universe together, playing a crucial role in its structure. While it cannot be detected by traditional means, since it neither emits, absorbs, nor reflects light or any form of radiation, its presence is inferred through its gravitational influence on visible matter. Without dark matter, the galaxies, stars, and other structures we observe would not exist in their current forms. The importance of dark matter is illustrated when scientists observe the rotation of galaxies. Galaxies appear to spin much faster than the visible matter within them should allow. There's simply not enough visible mass to keep them together, and yet they remain intact. Something unseen is at work, exerting a gravitational pull strong enough to hold them together, and that something is dark matter. It's like the invisible glue that shapes the universe, holding galaxies together and preventing them from flying apart due to the tremendous speeds at which their stars move. But dark matter is just one piece of the puzzle. The universe is also dominated by an even more mysterious force: dark energy. Comprising a staggering 68% of the universe's total energy content, dark energy is responsible for the accelerated expansion of the universe. Unlike dark matter, which pulls galaxies together, dark energy pushes them apart, accelerating the expansion at an ever-increasing rate. Although scientists have a basic understanding of dark energy's effects, they still do not fully grasp what it is or how it operates. In total, scientists have determined that visible matter, everything we can see with our telescopes, including stars, planets, and galaxies, makes up only about 5% of the universe. A much larger portion, around 27%, is dark matter, and the remaining 68% is dark energy. So, much of the universe consists of invisible forces that we can't directly perceive. These unseen forces are shaping the cosmos in ways we're only beginning to understand. The quest to uncover the nature of dark matter has been ongoing for decades. While scientists cannot detect dark matter directly, they know it exists because of the way it affects galaxies. Observations of galaxies show that they spin much faster than the visible matter alone should allow, which suggests the presence of an unseen mass. Without dark matter, these galaxies would not have enough gravitational pull to hold themselves together. To solve the dark matter puzzle, scientists are looking to the earliest moments of the universe. Shortly after the Big Bang, the universe was filled with hot plasma and energy, but dark matter played a pivotal role in forming the very first galaxies, stars, and clusters. Its gravitational pull acted as a framework by gathering gas and dust into dense regions where galaxies could form. Without dark matter, the universe might have been too diffuse, too sparse for galaxies to ever coalesce. Despite its fundamental role in shaping the universe, dark matter remains one of the greatest mysteries in science. What is it made of? Is it composed of particles we have yet to discover? Or could it be tied to forces that challenge our current understanding of physics? Scientists have turned to particle detectors, space telescopes, and advanced technologies in their search for answers. With each new experiment, they come closer to unraveling this cosmic riddle, but the truth continues to evade them. One of the most promising leads in the search for dark matter lies in the study of the cosmic microwave background, CMB. This faint radiation is a remnant of the Big Bang, a snapshot of the universe's early moments, and it serves as a kind of time capsule. By studying tiny fluctuations in the CMB, scientists have found indirect evidence that dark matter must have been present in the early universe, shaping the formation of galaxies and other large structures. Though dark matter remains invisible, its gravitational pull is tangible, pulling regular matter together and allowing the universe to evolve into the complex and vast structure we observe today. Ultimately, the hunt for dark matter is not just about solving a scientific mystery. It's about unlocking deeper truths about the nature of the universe itself. If scientists can uncover the true nature of dark matter, it could rewrite our understanding of the cosmos, offering new insights into the forces that govern its existence, and perhaps even revealing unknown realms of physics. Each new discovery brings us closer to understanding not only what dark matter is, but also how the universe came to be and how it will evolve in the future. Until then, the mysteries of dark matter and dark energy will continue to challenge our understanding, pushing the boundaries of science and human knowledge. Right now, scientists are working relentlessly to directly detect the elusive and mysterious substance known as dark matter. The pursuit is not just limited to studying its indirect effects, such as how it influences the movement of galaxies, but also to finding physical particles or signals that could finally reveal the true nature of this unseen force. Every new discovery, whether it's an observation or a failed experiment, brings us one step closer to unraveling one of the most profound and enigmatic mysteries in modern physics. In the very beginning, the universe was an incredibly chaotic and turbulent place, brimming with intense energy and matter. After the Big Bang, the universe was an inferno of heat and density, with particles speeding in all directions. As the universe gradually cooled, these particles started to come together, forming the first atoms and the most basic building blocks of matter. But this was no easy feat. Imagine the early universe as a gigantic boiling cauldron of particles. There had to be some invisible force that helped bring order to this chaotic soup of matter and energy. Something to help organize it, to give it structure. This is where dark matter plays its pivotal role. Even though dark matter is completely invisible to the naked eye, it had already begun to spread throughout the universe in immense quantities as the cosmos cooled and began to take shape. Dark matter began to clump together due to its powerful gravitational pull, like a force that acted like a cosmic architect, guiding the formation of galaxies, stars, and other cosmic structures. These clumps of dark matter not only helped shape the physical form of the universe, but also acted as a stabilizing agent. Without the influence of dark matter, the universe might not have been able to form the vast galaxies and clusters of stars that we observe today. Dark matter, in essence, worked as a cosmic blueprint, determining how galaxies grew, how they interacted, and how they held themselves together over billions of years. One of the most fascinating aspects of dark matter is its ability to form what are called dark matter halos. These halos are immense, invisible clouds of dark matter that surround galaxies, acting almost like a protective shield. They play an essential role in the stability of galaxies, preventing them from spinning apart under their own centrifugal force. Scientists believe that every galaxy, including our very own Milky Way, is surrounded by such a dark matter halo. The discovery of these halos was a groundbreaking moment in scientific history, not only confirming the existence of dark matter, but also revealing its crucial role in the structure and stability of galaxies. Without these halos, galaxies might not survive for long periods, and the universe might look very different. A key breakthrough in our understanding of dark matter came with the discovery of gravitational lensing. This occurs when the gravity of a massive object, such as a galaxy or a galaxy cluster, bends the light of objects located behind it. Think of it like a cosmic magnifying glass. When light from distant stars or galaxies passes through a massive cluster, the gravitational pull of that cluster bends the light, distorting it. By studying these distortions, scientists can infer how mass is distributed in the universe, even when that mass is invisible. This bending of light, known as gravitational lensing, is one of the most compelling pieces of evidence pointing to the existence of dark matter. Through this method, scientists have been able to identify large concentrations of invisible mass, what they believe to be dark matter, spread across galaxy clusters. Gravitational lensing is not only a fascinating phenomenon, but also one of the most effective ways to map out the presence of dark matter. By carefully analyzing how light from distant stars and galaxies is distorted, researchers can pinpoint where dark matter resides within galaxy clusters. This has allowed scientists to paint a clearer picture of how dark matter is distributed across the universe and how it affects the formation and evolution of galaxies. But while indirect evidence like gravitational lensing is critical, scientists are also on the hunt for something much more tangible: the actual particles that make up dark matter. These particles are theorized to interact only very weakly with ordinary matter, making them incredibly difficult to detect. The leading candidates for these elusive particles are known as WIMPs, weakly interacting massive particles. To catch a glimpse of these mysterious particles, scientists have set up various experiments in highly controlled environments. Detectors are placed deep underground to shield them from cosmic radiation, while others are positioned at the Large Hadron Collider, LHC, one of the most powerful particle accelerators on Earth. Despite the immense efforts, no one has yet directly detected dark matter particles, but this search is far from over. Each failed attempt to capture dark matter particles brings scientists one step closer to understanding what dark matter truly is. Even the smallest breakthrough could be a monumental leap forward in answering one of the universe's greatest questions. Dark matter is a fundamental mystery that holds the key to understanding the entire cosmos. Though we cannot directly observe it, we know it must exist because of the way it affects everything around it, especially the large-scale structures of the universe. Through careful study of distant galaxies, the cosmic microwave background radiation, CMB, and gravitational lensing, scientists have gathered compelling evidence for the presence of dark matter. These discoveries not only help us understand the universe's past, but also offer glimpses into its future. As we continue to unravel the mysteries of dark matter, we are also uncovering the basic forces that govern the entire universe. Dark matter is not just a key to understanding how galaxies were formed, but also to understanding the grand cosmic narrative, how the universe has evolved, and what its ultimate fate might be. It is possible that dark matter is related to other mysterious forces, such as dark energy, which is responsible for the accelerated expansion of the universe. By studying dark matter in depth, scientists hope to uncover some of the universe's most profound secrets, potentially changing our understanding of everything we know about the cosmos. Yet, despite the tremendous progress made, the study of dark matter is far from complete. In fact, we are only scratching the surface. Over the coming decades, scientists are developing even more sophisticated tools and experiments to detect dark matter particles and understand their true nature. With the advent of new technologies and space missions, such as the JAMES WEBB Space Telescope, there is hope that we may soon be able to peer deeper into the universe than ever before, observing distant galaxies and cosmic events that were previously beyond our reach. These missions will offer us an unparalleled view of how dark matter influences the formation and organization of galaxies, as well as the structure of the universe as a whole. Meanwhile, on Earth, scientists are developing cutting-edge detectors that will be placed in extreme locations, such as deep underground or even in space, to search for the faintest traces of dark matter's presence. These detectors are highly sensitive and designed to detect the rarest of interactions between dark matter particles and ordinary matter. With each new experiment, each new breakthrough, we come one step closer to solving the puzzle of dark matter. Though we cannot yet see dark matter with our eyes, its effects are undeniable. It plays a monumental role in shaping the structure of the universe, influencing the formation of galaxies, stars, and even the very fabric of space itself. The search for dark matter particles is one of the most exciting scientific endeavors of our time, as it holds the potential to answer some of the most profound questions about the nature of reality. The journey to uncover the secrets of dark matter is just beginning, and as research accelerates, the discoveries we make in the coming years could transform our understanding of the cosmos. Another pivotal mystery lies in the ancient history of the universe, the discovery of the very first stars. These stars, known as population 3 stars, were formed shortly after the Big Bang, during a time when the universe was still in its chaotic infancy. They were composed almost entirely of hydrogen and helium, the simplest elements in existence, and their formation marks a monumental moment in cosmic history. Thanks to advanced telescopes like the James Webb Space Telescope, JWST, scientists are now able to study these ancient stars, offering a rare glimpse into the universe's primordial past. The birth of these stars occurred just a few 100 million years after the Big Bang, during a period when the universe was still hot and dense. In the aftermath of the Big Bang, only the simplest elements, hydrogen and helium, existed in abundance. These two elements formed the building blocks of everything we see today. Hydrogen, the most abundant element in the universe, consists of single atoms, each containing just one proton. Helium, the second lightest element, consists of 2 protons and 2 neutrons. These two elements were the foundation for the first structures in the universe, yet heavier elements like carbon, oxygen, and iron had yet to form. The universe in this early era was dark and silent, a vast emptiness devoid of stars, galaxies, or any bright points of light. This period, known as the Cosmic Dark Ages, lasted for hundreds of millions of years. But even in this darkness, an invisible force was at work: gravity. Gravity began to pull together the clouds of hydrogen and helium, gradually compressing them under their own weight. As these clouds compressed, they grew hotter and denser, eventually triggering the birth of the first stars, which illuminated the universe and ended the long era of darkness. These first stars, known as population 3 stars, were unlike anything we see today. They were far more massive and hotter than modern stars, and they played a crucial role in shaping the universe's evolution. Their formation marks a pivotal moment in the history of the cosmos, one that we can now study in unprecedented detail with the help of cutting-edge space telescopes like JWST. These ancient stars offer us a window into the earliest moments of the universe's existence, a time when the universe was just beginning to emerge from the chaotic aftermath of the Big Bang. As we continue to study dark matter, the first stars, and the forces that shape the universe, we are slowly piecing together the grand narrative of cosmic history, a narrative that stretches back billions of years and continues to unfold with each new discovery. The journey is far from over, but with each step forward, we come closer to understanding the profound mysteries of the universe and our place within it. The first stars in the universe, the ancient giants that arose in the wake of the Big Bang, were unlike anything we see today. Enormous, blazing with heat and composed primarily of hydrogen and helium, these were the original building blocks of the cosmos. Astronomers refer to them as population 3 stars, marking them as the first generation to emerge after the birth of the universe, distinct from the stars that came later, which contained heavier, more complex elements. The role these stars played in shaping the universe cannot be overstated. They were the first beacons of light in an otherwise dark, formless expanse. This epoch, known as cosmic reionization, marks one of the most transformative events in the history of the universe. Before these stars ignited, the cosmos was filled with a dense fog of neutral hydrogen gas, which absorbed light, preventing it from traveling freely across space. The birth of population 3 stars shattered this silence. Their radiant energy, released in the form of intense ultraviolet radiation, ionized the hydrogen gas around them. This meant that the gas was stripped of its electrons, transforming it from opaque to transparent. For the first time in the history of the universe, light could travel freely, and the cosmos began to take on its current form, a process that forever changed how we perceive space. These early stars were nothing short of colossal. Their sizes were often hundreds or even thousands of times greater than our sun. Such immense mass meant they burned through their nuclear fuel at an astonishing rate. While stars like our sun can live for billions of years, these ancient giants existed for only a few million years, a blink of an eye in the cosmic timeline. Their lives were brief but incredibly dramatic, ending in catastrophic explosions known as supernovae. These supernovae were not just the death of stars, but the birth of new elements, iron, gold, and other heavier elements that are essential for the formation of planets and life itself. The death throes of population 3 stars scattered these elements across the cosmos, enriching the universe with the building blocks necessary for the creation of new stars, planets, and eventually life. These explosions marked the beginning of a new era, one where the death of stars gave rise to new worlds. In this sense, their death was not an end, but the very beginning of everything we know today. However, studying these ancient stars is one of the most challenging endeavors in modern astronomy. The main difficulty lies in their extreme distance from us. These stars were formed billions of years ago, and the light they emitted had to travel vast distances across space to reach Earth. By the time that light finally arrives, it is incredibly faint and difficult to detect. As a result, astronomers rarely observe these stars directly. Instead, they rely on indirect clues, such as the effects these stars had on their surroundings. One of the most significant clues comes from the ionization of the gas surrounding these stars. As the intense radiation from population 3 stars ionized the hydrogen gas, it could have created massive bubbles of ionized hydrogen. These bubbles would have been vast, their size and spread offering key insights into the nature of the stars responsible for them. By carefully analyzing the distribution of these bubbles, scientists can infer much about the characteristics of these stars, shedding light on the universe's earliest moments. The study of population 3 stars goes beyond just understanding the distant past of the universe. These stars were the first to create the heavy elements, carbon, oxygen, iron, that are essential for the formation of planets and eventually life. Without these first stars, there would have been no raw materials to form the planets, stars, and other structures we see in the universe today. By studying these ancient stars, we can begin to unravel the conditions that led to the formation of the very first planets and, in time, the rise of life itself. Population 3 stars are crucial not only for understanding the origins of life, but also for understanding the larger evolution of the universe. These stars played a key role in the formation of galaxies, black holes, and other large-scale structures that populate the cosmos. Their explosive deaths seeded the universe with the heavy elements that would later form the building blocks of galaxies and stars. By studying their life cycles, from their birth to their violent end, scientists are piecing together the story of how the universe evolved over the course of 13.8 billion years. Each new discovery about these stars brings us one step closer to understanding the intricate processes that have shaped the universe. The James Webb Space Telescope, JWST, with its revolutionary capabilities, is currently unraveling more mysteries about the early universe than ever before. JWST's ability to peer into the past has opened a window into the earliest moments of the universe, allowing scientists to study these first stars in greater detail. This telescope has already provided insights into the birth of the first galaxies and stars, and it continues to push the boundaries of our understanding. Looking forward, the next generation of telescopes and observatories will build upon the groundbreaking discoveries made by JWST. As technology advances, there is hope that we may one day be able to directly observe the remnants of these very first stars. Finding the relics of Population 3 stars would be like opening a time capsule, a direct link to the earliest moments of the universe, just after the Big Bang. The study of Population 3 stars represents one of the most thrilling frontiers of modern astronomy. These stars, formed in the infancy of the universe, were composed solely of hydrogen and helium, elements that existed in abundance just moments after the Big Bang. In many ways, they are the ultimate pioneers in the cosmic story. They not only lit up the dark void of space, but also gave birth to the elements that would go on to form everything we know today. Thanks to advances in technology, we now have the ability to peer deeper into the past than ever before. The discoveries made by the James Webb Space Telescope are already rewriting our understanding of the universe's early stages. This breakthrough gives us a glimpse into the conditions that led to the formation of the first stars and galaxies, and the elements that would eventually give rise to life as we know it. As we continue to explore the mysteries of the cosmos, the study of Population 3 stars promises to inspire and captivate scientists and astronomers for generations to come. In the grand tapestry of the universe, the creation of heavy elements is a crucial chapter. These elements were forged in the hearts of the first stars through a process known as nucleosynthesis, where atomic nuclei fuse together under immense pressure and heat. The heaviest elements in the universe, like gold and platinum, were created through a specific type of nucleosynthesis that occurs when neutron stars collide or explode in supernovae. This process, known as the Rapid Neutron Capture Process, or R process, is responsible for creating the elements that are essential for life. The very first atomic nuclei were formed within minutes of the Big Bang through a process known as Big Bang nucleosynthesis. By the time the universe was 20 minutes old, it had expanded and cooled enough for high-energy collisions between particles to slow down. As a result, only the simplest elements, hydrogen and helium, were formed, with trace amounts of other elements like lithium and deuterium. Over time, stars formed and began the process of stellar nucleosynthesis, creating heavier and heavier elements through their life cycles. Eventually, the violent deaths of these stars, through supernova, scattered these elements into the cosmos, enriching the universe with the material needed for the formation of planets and life. This ongoing cycle of stellar birth, life, death, and rebirth has shaped the cosmos over billions of years, leading to the complex, element-rich universe we observe today. The study of these processes, particularly the role of Population 3 stars, provides us with a deeper understanding of how the universe came to be, and the incredible journey from hydrogen and helium to the rich tapestry of elements that form the very fabric of our existence. The universe, in its vast expanse, is largely composed of hydrogen and helium, the two lightest elements. These elements, known as the building blocks of the cosmos, make up a staggering majority of the observable matter. In fact, heavier elements, or what astrophysicists refer to as metals, constitute only a tiny fraction of the universe's total mass. Stars, the cosmic factories where elements are born, are the primary means by which these metals come into existence. Within their cores, lighter elements undergo fusion, transforming into heavier ones while releasing vast amounts of energy. This process, known as stellar nucleosynthesis, is the heart of a star's power. Through these fusion reactions, lighter elements like hydrogen, helium, and lithium fuse to form heavier ones, including iron and nickel, especially in the most massive stars. However, the products of these nuclear reactions don't just escape the star's core immediately. They are typically trapped inside unless they are later ejected through stellar winds or violent explosions. As the fusion process intensifies, the most massive stars experience explosive events known as supernova, marking a dramatic turning point in the creation of new elements. Supernovae are responsible for producing a host of elements, especially those heavier than iron. These explosions not only eject elements formed during the star's lifetime, but they also trigger intense nucleosynthesis within the blast itself. This is where processes like the R process, rapid neutron capture, and the S process, slow neutron capture, come into play. The R process, in particular, occurs when neutrons are rapidly absorbed by atomic nuclei during the explosion, creating even heavier elements in the process, such as gold, platinum, and uranium. The intense energy from a supernova catalyzes these reactions, turning what was once a peaceful, fusion-powered star into a violent cosmic furnace, creating new elements in the blink of an eye. In recent years, another remarkable discovery has reshaped our understanding of element formation: neutron star mergers. When two neutron stars, dense remnants of once massive stars, collide, the resulting explosion releases an immense amount of neutron-rich matter. This rapid release of neutrons provides the perfect environment for the R process to occur, forming a substantial amount of heavy elements. This violent event not only creates new matter, but also leaves behind an imprint of its explosive origin, further enriching the universe with even more complex elements. Yet, stellar processes aren't the only means by which elements are created. High-energy cosmic rays, which travel through space at nearly the speed of light, also play a role in element formation. This process, known as cosmic ray spallation, happens when these energetic particles collide with atomic nuclei, breaking them apart into lighter elements. The creation of elements like helium-3, beryllium-9, and boron isotopes, elements not typically produced by stellar nucleosynthesis, occurs in this process. Cosmic ray spallation can take place anywhere, from space itself to asteroids and even here on Earth, in our atmosphere and soil. This phenomenon is a key contributor to the cosmogenic nuclides that we find on Earth, which offer scientists valuable clues about the processes that occur throughout the cosmos. Another intriguing process that contributes to the formation of elements on Earth is radiogenesis. This occurs when long-lived ancient radioactive elements such as uranium, thorium, and potassium-40 undergo radioactive decay over the course of billions of years. Through this decay, they produce new atomic nuclei, contributing to the creation of a variety of elements found on our planet today. Looking further back in time, we arrive at the dawn of the universe itself. Approximately 13.8 billion years ago, in the aftermath of the Big Bang, the universe was a hot, dense, and chaotic place. The first atomic building blocks, protons and neutrons, formed from a superheated quark-gluon plasma, and as the universe cooled, these particles combined to form the first atomic nuclei. This era, known as Big Bang nucleosynthesis, was crucial for the creation of the first primordial elements, including hydrogen, helium, and trace amounts of lithium and beryllium. However, the conditions were not yet ripe for the formation of heavier elements like carbon. During the early stages of the universe's evolution, these light elements, hydrogen, helium, lithium, and beryllium, were the primary building blocks available for further element formation. The heavier elements, such as carbon, could not form during the Big Bang. Instead, they began to emerge later, as the universe continued to cool and stars began to form. Over millions of years, cosmic rays, primarily composed of high-energy protons, collided with interstellar gas and dust, breaking apart heavier elements and forming new light elements such as helium-3, lithium, beryllium, and boron. The creation of carbon marked another major milestone in the evolution of elements. Unlike the lighter elements created in the Big Bang, carbon could not form under the conditions that existed in the early universe. Instead, it was produced later in the cores of larger stars through a process known as the triple alpha process. In this high-pressure environment, 3 helium nuclei, alpha particles, fused together to form carbon. This crucial step in element formation took place around 500 million years after the Big Bang, marking the beginning of the cycle that would lead to the creation of even heavier elements. As the universe continued to evolve, the process of creating heavier elements, or nucleosynthesis, required increasingly extreme conditions, high temperatures and pressures. These conditions are found in the cores of stars, where nuclear fusion is constantly at work. The first stars, which formed approximately 500 million years after the Big Bang, were the first to generate these extreme conditions. Over time, as new stars formed in galaxies, heavier elements were produced and spread throughout the universe, enriching the cosmos with the diversity of elements that we observe today. The primordial nuclides, the earliest chemical elements formed in the universe, were produced by a variety of processes: Big Bang nucleosynthesis, stellar nucleosynthesis, supernova, and even rare events like neutron star mergers. Some elements, such as argon-40, were formed later through radioactive decay, adding another layer of complexity to the chemical composition of the universe. Over billions of years, Earth's geological processes, including mixing and evaporation, have altered these original elements into the natural composition we observe today. The heavier elements, which appeared after the Big Bang, range from carbon to plutonium. These elements were created through nuclear reactions that involved the strong and weak nuclear forces, in a process known as nuclear fusion. This includes both rapid and slow neutron capture, as well as processes like nuclear fission and radioactive decay, such as beta decay. The stability of atomic nuclei, determined by the balance of protons and neutrons, greatly influences how these reactions occur, making the study of cosmic nucleosynthesis a critical field for researchers in astrophysics and nuclear physics, a discipline often referred to as nuclear astrophysics. In the early days of scientific inquiry, many believed that all the chemical elements were created at the beginning of the universe. Yet, as our understanding deepened, it became clear that hydrogen and helium were by far the most abundant elements in the universe. Together, these two elements make up almost everything we see in the cosmos, with all other elements accounting for less than 2% of the total mass in our solar system and beyond. Oxygen and carbon were found to be the next most common elements, and it became evident that lighter elements, especially those formed from helium-4 nuclei, known as alpha nuclides, were far more prevalent than previously thought. In 1920, British astrophysicist Arthur Stanley Eddington made a groundbreaking proposal that would change the course of scientific understanding. He suggested that stars generate their energy by fusing hydrogen into helium, and that in doing so, they may also produce heavier elements. This idea, which would later be confirmed through extensive research, laid the foundation for our understanding of stellar nucleosynthesis and the creation of the chemical elements that make up everything we know. Thus, from the fiery hearts of stars to the explosive violence of supernovae and the mysterious collisions of neutron stars, the story of element creation in the universe is one of continuous evolution and discovery. Through each of these processes, the elements that make up our world and ourselves are forged in the crucible of cosmic events that stretch back to the very beginning of time. The idea of how elements are created in the universe has long been a subject of intense scientific exploration, though it wasn't always widely accepted. Early on, scientists were unsure about the nuclear processes that could account for the formation of elements, as much of the underlying mechanisms remained a mystery. This uncertainty persisted until just before World War II, when a breakthrough occurred. It was at this time that the German scientist Hans Bethe finally provided a comprehensive explanation of how hydrogen fuses into helium through nuclear reactions. Bethe's work laid the foundation for understanding stellar nucleosynthesis, a term used to describe the formation of elements within stars. After the war, Fred Hoyle made significant contributions to the understanding of how heavier elements are created in stars. His pioneering research explained the process by which elements heavier than hydrogen could form, eventually leading to the formation of all the elements found in nature. Hoyle also proposed a radical idea that hydrogen is constantly being created in the universe from the vacuum of space and the energy contained within it, without requiring any initial starting point. His theory also described how the abundance of elements in the universe increases over time as galaxies age, a concept that was vital for explaining how the chemical makeup of the cosmos evolves. Hoyle's work was expanded upon in the 1960s by scientists like William A. Fowler, Alistair G. W. Cameron, and Donald D. Clayton. These researchers made further strides in our understanding of stellar nucleosynthesis, describing how elements heavier than hydrogen were formed through complex nuclear processes inside stars. A landmark paper published in 1959 by I.B. Burbage, G.R. Burbage, Fowler, and Hoyle helped consolidate these ideas, laying out in detail the mechanisms that create heavy elements and how these processes could be studied by astronomers. While this research was underway, the concept of the Big Bang emerged. In 1931, Belgian physicist Georges Lemaitre proposed that the universe began from a single point he called the primeval atom. He theorized that if we could trace the expansion of the universe backward in time, we would eventually arrive at this initial point, where both time and space as we know them did not yet exist. This radical idea of an expanding universe challenged conventional thinking about the cosmos. In 1949, Fred Hoyle, while broadcasting a BBC radio program, coined the term Big Bang to describe this theory. Although he denied the term was meant as an insult, it quickly became synonymous with the origin of the universe, in stark contrast to other competing theories. Lemaitre's theory was instrumental in explaining the observed high levels of helium in the universe, as well as the existence of deuterium and other elements between helium and carbon. These elements were found not only in stars, but also in the vast spaces between them, called the interstellar medium. Together, Lemaitre's and Hoyle's theories helped piece together the puzzle of how the universe's elements were created, providing a key understanding of the composition of the cosmos. One of the major scientific developments in this field came in the form of the theory of nucleosynthesis. This theory seeks to explain why different chemical elements and their isotopes are found in varying amounts in the universe, based on natural processes that take place in stars and other cosmic phenomena. A key reason the theory was developed came from the strange patterns observed in the abundance of elements across the periodic table. When the number of elements is graphed against their atomic number, the resulting chart looks like a jagged, sawtooth-like line, with some elements being far more abundant than others, by factors as great as 10 million. One of the most inflow breakthroughs in this research was the creation of an abundance table by scientists H. Sues and Harold Urey. This table was based on the unchanged abundance of elements found in meteorites that had undergone little to no transformation over time. The table displayed these values on a logarithmic scale, which helped smooth out the sharp peaks and valleys caused by the vast differences in abundance levels. It was a pivotal step in advancing the study of how elements are distributed throughout the universe. Most of the processes that lead to nucleosynthesis occur inside stars, with various types of nuclear fusion helping to create different elements. The process of hydrogen burning in stars, for example, can occur via two primary methods, the proton-proton chain and the CNO cycle. Both of these processes ultimately lead to the formation of heavier elements. As stars evolve, they go through stages of burning, with elements such as helium, carbon, neon, oxygen, and silicon being formed along the way. During these stages, the star creates elements up to the atomic weight of iron and nickel. These elements are especially stable, making them the final products of stellar nucleosynthesis. However, for elements heavier than iron, the process becomes more complex. There are various methods of formation, such as neutron capture, which is known as the S process. In this process, neutrons are slowly captured by atomic nuclei, transforming them into heavier elements. But in more extreme conditions, like during a supernova explosion or when neutron stars merge, other processes come into play. These include the R process, which occurs when neutrons are rapidly captured, as well as the P process, also called the gamma process, in which nuclei are broken apart by high-energy photons. Stellar nucleosynthesis is not only responsible for creating the elements we see today, but it also explains how those elements are spread throughout the universe. As stars age and lose mass, they expel elements into space through powerful stellar winds. In smaller stars, this happens during the planetary nebula phase, while in more massive stars, it occurs at the end of their life cycle when they explode in a supernova. These explosive events are crucial for dispersing heavy elements throughout the galaxy, seeding the interstellar medium with the building blocks of new stars, planets, and life. The first solid evidence that stars are responsible for creating elements came from observations showing that the interstellar gas from which new stars are born became enriched with heavier elements over time. This meant that stars born later in the galaxy contained more heavy elements than those born earlier. In 1952, scientists discovered technetium in the atmosphere of a red giant star, further proving the concept of stellar nucleosynthesis. Technetium, being radioactive and decaying quickly, could only have been produced recently, providing direct evidence that nuclear reactions were happening inside the star. More evidence came when astronomers found large quantities of barium in certain stars, particularly those located on the asymptotic giant branch. The high concentration of barium in these older stars suggested that the S process was at work, converting lighter elements into heavier ones. These discoveries further confirmed that stars are not just shining bodies of gas, but complex nuclear reactors that play a crucial role in the evolution of the universe and the formation of the elements that make up everything we see around us. The universe is a vast, intricate tapestry, woven together by forces and processes that are often invisible to the naked eye. But within this cosmic expanse, there are tiny clues, minute pieces of matter, that help scientists piece together the story of our universe's formation and evolution. Among these clues, one of the most fascinating and revealing is stardust. Stardust is not just a poetic term. It is made up of tiny grains of material that have traveled across vast distances, carrying with them the legacy of stars long since gone. These grains, often found in meteorites, are referred to as pre-solar grains because they formed long before our sun came into existence. By studying these minute particles, scientists gain valuable insights into the life cycles of the stars that created them. The isotopic composition of stardust provides clues about the nuclear processes that unfold in the hearts of stars, revealing how elements are forged during a star's violent death throes. One of the most significant processes that scientists study through stardust is stellar nucleosynthesis. This term refers to the creation of elements inside stars, particularly during their final stages. Supernova nucleosynthesis, occurring in the explosive environment of a supernova, is a process that creates elements heavier than iron, such as those between silicon and nickel. In the intense heat and pressure of a supernova, nuclear reactions occur at an unprecedented rate, rapidly bonding with silicon-28 nuclei. This process, known as quasi-equilibrium, is almost stable but filled with an abundance of silicon, driving the formation of these intermediate elements. It was a crucial breakthrough in our understanding of how these elements are produced, replacing an earlier flawed theory proposed in the famous B2FH paper. However, the formation of elements does not stop with silicon and nickel. There's another fascinating aspect of nucleosynthesis that scientists continue to explore: the R process, or rapid neutron capture process. This process occurs when atomic nuclei capture neutrons at such a rapid pace that it results in the creation of elements even heavier than nickel, elements like uranium and thorium. For a long time, it was believed that the R process could only happen in stars made up of more complex elements. But groundbreaking research revealed that even the simplest stars, those composed primarily of hydrogen and helium, could undergo the R process and create these heavy elements. The evidence for this came from the study of ancient stars, particularly those found in galaxies with low metallicity or minimal heavy elements. These stars still contained R process elements, proving that this process occurs not only within specific types of stars, but can take place across a range of environments in the universe. But the R process is not the only way stars create elements. There's also the RP process, or rapid proton process, which involves the rapid absorption of protons instead of neutrons. While this process is not as well understood as the R process, it's thought to play a role in the creation of certain elements under extreme conditions, such as those found in a supernova explosion. As stars evolve and explode, they undergo dramatic transformations. During these supernova, nuclear fusion plays a pivotal role in shaping the periodic table. For example, when oxygen and silicon nuclei fuse, they form nuclei that balance protons and neutrons, creating stable isotopes like calcium-40. However, heavier isotopes, those with an equal number of protons and neutrons, are unstable and decay after the explosion, leaving behind more stable elements such as iron-56, chromium-52, and titanium-48. This process of decay releases gamma radiation, which can be detected by scientists as part of gamma-ray astronomy. These emissions help astronomers identify the specific elements formed during a supernova and were key to confirming the theory of explosive nucleosynthesis. One of the most striking confirmations of these theories came from the 1987 supernova, in which gamma-ray lines were detected coming from the explosion. These lines revealed the presence of radioactive elements like cobalt-56 and cobalt-57, directly linking supernovae to the creation of these elements. This discovery was a major milestone in the development of nuclear astronomy and helped to shape future missions like NASA's Compton Gamma Ray Observatory. Yet, the evidence for supernova creating heavy elements doesn't end there. As these stellar explosions unfold, they produce not just radiation but also stardust grains, which form as the supernova expands and cools. These grains become part of cosmic dust, and by studying them, scientists can confirm that supernovae are crucial to the formation of new elements in the universe. For instance, titanium-44, an isotope found in these grains, provided further confirmation of the role that supernovae play in nucleosynthesis. However, while supernovae are some of the most dramatic events in the universe, they are not the only sources of cosmic material. Between galaxies, there exists an enigmatic phenomenon: intergalactic gas clouds. These clouds, composed mostly of hydrogen and helium, float through the vast emptiness of space, far removed from the energy of stars or the gravitational pull of galaxies. Despite their elusive nature, these clouds are critical for understanding the universe's evolution. The intergalactic medium, as these clouds are known, is not as dense as the gas found within galaxies. In fact, it's often so diffuse that it's nearly invisible to the naked eye. Yet, through careful observation of how light interacts with these clouds, scientists can detect their presence and infer their characteristics. These clouds are thought to be remnants from the early days of the universe, holding essential clues about the universe's infancy and how it transitioned from a hot, dense state to the cooler, more expansive cosmos we observe today. Right after the Big Bang, the universe was an incredibly hot and dense place, essentially a boiling cauldron of gas and energy. As the universe began to expand, it cooled down, allowing the gas to spread out and eventually form the first stars. These stars became the first beacons of light in an otherwise dark cosmos, gathering together to form the first galaxies. But not all of the gas that existed in the early universe formed stars. A significant portion of it remained scattered across the universe, lingering in the intergalactic medium. Today, this gas is still present, drifting between galaxies. It's a relic of the universe's early history, and studying it can provide insights into the birth and evolution of galaxies. The intergalactic gas clouds are like time machines, offering a glimpse into the past and helping scientists unravel the mysteries of the universe's evolution, from the first moments after the Big Bang to the ongoing formation of galaxies, stars, and planets. As we continue to study stardust, supernovae, and intergalactic gas clouds, the universe's vast narrative slowly becomes clearer. Each grain of dust, each flash of gamma radiation, and each drift of gas between galaxies is a small yet essential part of a much larger story, a story that stretches back billions of years and continues to unfold, revealing the deep and ever-expanding mysteries of the cosmos. The universe is a vast and complex place, and the more we study it, the more we uncover the intricate details of its past and present. Among the most intriguing and essential components of the cosmos are intergalactic gas clouds. These seemingly elusive clouds, composed primarily of hydrogen and helium, play a central role in many of the most significant processes that have shaped the universe as we know it. By examining these clouds, scientists can peer into the deepest history of the universe, learning how stars were born, how galaxies formed and evolved, and how the universe itself grew and changed over billions of years. Intergalactic gas clouds are far from being random, isolated objects floating aimlessly through space. Rather, they are the foundational building blocks for much of the matter in the cosmos. Without these clouds, the universe would be a very different place, one devoid of galaxies, stars, or planets. These clouds serve as the raw material from which everything we observe in the universe emerges. Understanding how they function and how they interact with galaxies and stars reveals the very mechanisms that have driven the evolution of the cosmos. One of the most fascinating processes in the universe is the birth of stars, and intergalactic gas clouds are crucial to this process. These clouds are mostly made up of hydrogen, the lightest and most abundant element in the universe. Under the influence of their own gravity, these clouds slowly begin to collapse inward, drawing the gas particles closer together. As the gas becomes more compressed, the temperature within the cloud increases dramatically. When the temperature reaches a certain threshold, nuclear fusion ignites and a new star is born. This entire process, from the initial collapse of the gas cloud to the formation of a blazing, radiant star, can take millions of years. During this long journey, the cloud undergoes dramatic transformations, shifting from a cold, diffuse mass of gas into a hot, dense ball of energy. The birth of a star is not just a single event, but the culmination of countless physical processes, each step carefully orchestrated by the laws of physics. Most stars form within the dense cores of galaxies, but some, known as intergalactic stars, form outside the boundaries of galaxies, in the vast voids between them. These rogue stars provide valuable insights into the early universe, offering a glimpse into the conditions that existed before galaxies began to take shape. The study of these rogue stars can help scientists understand the conditions that prevailed in the early cosmos, long before the first galaxies formed. These intergalactic clouds offer clues about the environment in which the earliest stars were born. By analyzing how these clouds collapsed and formed stars, researchers can piece together the history of the universe, uncovering the processes that shaped the cosmic landscape over billions of years. Gas clouds are not only vital for star formation, but also play a crucial role in the growth and evolution of galaxies. Over time, galaxies expand by gathering gas from the surrounding space, a process known as accretion. This gas, often drawn from vast intergalactic clouds, is the fuel that allows galaxies to grow larger. As galaxies accumulate more gas, new stars begin to form, breathing new life into the galaxy. The more gas a galaxy collects, the larger it becomes, and the more stars it can produce. However, galaxies don't simply grow in size. They also undergo dramatic changes throughout their lifetimes. Some galaxies collide with one another, merging to form even larger galaxies. During these cosmic crashes, the gas clouds from the colliding galaxies interact, triggering intense bursts of star formation. These starbursts provide valuable insights into the forces at work during galaxy mergers, helping scientists understand how galaxies evolve over time. By studying the interactions between gas clouds and galaxies, astronomers can gain a deeper understanding of the processes that drive galaxy evolution. The study of these interactions reveals not only how galaxies grow and change, but also the broader forces that govern the behavior of matter on cosmic scales. As galaxies collide, merge, and evolve, they offer a unique window into the dynamic and ever-changing nature of the universe. In addition to their role in star formation and galaxy growth, intergalactic gas clouds are also responsible for the creation of heavier elements, which are essential for the development of the universe as we know it. In the early universe, only the simplest elements, hydrogen and helium, existed. However, as stars formed and began to fuse lighter elements like heavier elements such as carbon, oxygen, and iron, the composition of the universe began to change. When these stars reached the end of their lives, many of them exploded in a spectacular event known as a supernova. These explosions scattered the newly formed heavier elements across space, seeding the surrounding gas clouds with these richer materials. Over time, the elements in these gas clouds mixed and combined, leading to the creation of even more complex elements. As new stars formed from these enriched clouds, they were made up of a broader array of elements than those in the early universe. This diversity of elements would go on to play a critical role in the formation of planets and, eventually, life itself. By studying the makeup of intergalactic gas clouds, scientists can trace the evolution of elements in the universe, piecing together a timeline of cosmic history. These clouds serve as a record of the chemical evolution of the cosmos, showing how the explosive deaths of stars, along with the mixing of elements in gas clouds, help shape the very universe we live in today. The elements created in these clouds are the building blocks for everything in the universe, from the stars in the sky to the planets beneath our feet. However, studying these intergalactic gas clouds is not an easy task. These clouds are faint, spread out over vast regions of space, and often hidden in parts of the universe that are difficult to observe. Their faintness makes them challenging to detect, and their distribution across vast areas of space makes them difficult to study in detail. But thanks to advancements in technology and improved observational methods, scientists have made tremendous progress in unraveling the mysteries of these distant clouds. Modern telescopes equipped with advanced detectors allow astronomers to capture light beyond the visible spectrum, providing a much clearer picture of the gas clouds that populate the universe. Unlike stars, which emit visible light, these clouds do not shine brightly. Instead, they emit faint radiation across a wide range of wavelengths, including ultraviolet and infrared light. By observing these wavelengths, scientists can gather crucial information about the composition, temperature, and density of these gas clouds, revealing secrets about the universe that were once beyond our reach. With these new tools, scientists are uncovering more about the nature of the universe than ever before. These discoveries are helping to fill in the gaps in our understanding of the cosmos, offering us a more complete picture of how stars, galaxies, and the universe itself came to be. The study of intergalactic gas clouds is one of the most exciting frontiers in modern astronomy, and as technology continues to advance, the secrets of these distant clouds will undoubtedly yield even more fascinating revelations about the universe and our place within it. In the boundless reaches of space, the interaction between light and the mysterious gas clouds scattered across the cosmos holds the key to unraveling some of the universe's deepest secrets. However, it's not just the visible light that reveals the essence of these clouds. Light in its many forms, from ultraviolet rays to radio waves, offers an intricate portrait of their composition, movement, and evolution. By studying how these clouds absorb and emit different wavelengths of light, scientists gain crucial insights into their temperature, density, and chemical makeup. This process allows us to peer into the very heart of the universe's vast and ever-changing structure, offering a window into a realm far beyond the limits of human sight. A cornerstone of this exploration is the Hubble Space Telescope, one of the most remarkable scientific instruments ever created. Since its launch into space, Hubble has served as a vital eye on the cosmos, transcending the capabilities of ground-based observatories. It doesn't just observe bright stars or familiar galaxies, but is specially designed to detect the faintest traces of light, revealing distant objects such as quasars, stars, and galaxies located billions of light years away. As light travels across the universe and passes through intergalactic gas clouds, these clouds absorb specific wavelengths, leaving behind a distinct fingerprint that scientists can meticulously analyze. This fingerprint tells a story, a detailed record of the cloud's temperature, chemical composition, and density. Without this information, which would be difficult to gather by any other means, our understanding of the cosmos would remain incomplete. Yet, Hubble is not the only tool that has expanded our vision of the universe. Radio telescopes, which detect radio waves emitted by the gases within these clouds, have become indispensable in this line of research. These radio waves are unique because, unlike visible or infrared light, they can pass through thick clouds of gas and dust that would typically obscure other forms of electromagnetic radiation. This ability allows scientists to study regions of space that would otherwise remain hidden from view. One of the most advanced radio telescopes, the Atacama Large Millimeter Submillimeter Array, ALMA, is located in the high-altitude deserts of Chile. ALMA is positioned in one of the driest places on Earth, giving it an unparalleled vantage point to study cold, dense gas that resides in intergalactic clouds. These clouds, often found in the space between galaxies, are not just empty regions. They are dynamic and crucial to the formation of galaxies, stars, and other celestial objects. By studying how gas clouds move, collide, and interact with one another over time, researchers can piece together the processes that shape the cosmos. ALMA's observations allow scientists to track the evolution of these clouds and investigate how they contribute to the formation and growth of galaxies, offering a deeper understanding of how the universe itself has evolved. In addition to observational tools like Hubble and ALMA, scientists also rely heavily on advanced computer simulations to further their understanding of gas clouds and their behavior. These simulations recreate conditions from the early universe, allowing scientists to model how gas clouds might have changed over billions of years. By comparing the results of these simulations with actual data collected from telescopes, researchers can test hypotheses and refine their theories about how galaxies, stars, and the universe itself came into being. These simulations are crucial for predicting future cosmic events, such as how clouds of gas might collide or merge with galaxies, thus helping scientists anticipate how the universe will continue to evolve in the distant future. The study of gas clouds is not just a technical exercise, it's a fascinating journey through time. These clouds are not just random accumulations of gas. Some of them are among the oldest objects we can observe, dating back billions of years. In essence, when we look at these clouds, we are looking back in time, observing the conditions of the universe when it was still young, chaotic, and in the process of forming the first stars and galaxies. These intergalactic gas clouds are like time machines, preserving the raw materials from which the universe was built and providing us with a snapshot of its earliest days. For scientists, these ancient clouds are akin to fossils, except rather than preserving bones or organic matter, they hold the chemical fingerprints of the universe's youth. By analyzing the composition of these gases, researchers can trace the origins of the first elements, hydrogen, helium, and the heavier elements formed in stars, which would eventually give rise to stars, planets, and everything else in the universe. Understanding how these elements were forged in the first few moments after the Big Bang and how they evolved in subsequent generations of stars is key to understanding the cosmic history of matter itself. Furthermore, scientists examine how these gas clouds have interacted with galaxies over time. Galaxies, massive collections of stars, dust, and gas, are constantly evolving, and the gas clouds play a critical role in this process. As gas clouds are drawn into galaxies, they contribute to their growth and transformation. By studying how these clouds have influenced the development of galaxies, scientists can trace the evolution of galaxies from simple, isolated objects to the complex systems of stars and planetary systems we see today. The movement and merging of these gas clouds within galaxies has played a crucial role in shaping the structure of the universe. By comparing the gas clouds from the earliest periods in the universe with those that formed later, scientists can build a timeline of cosmic history, one that stretches from the explosive birth of the universe, filled with dense, hot gas and energy, to the formation of the first stars, galaxies, and ultimately the vast, complex universe we inhabit today. This comparison is akin to looking through a photo album, where images taken at different times reveal how a place has changed over the course of billions of years. With each new piece of data from these clouds, we unlock another layer of the story of the universe's origin and evolution. Intergalactic gas clouds are far from being mere voids in space. While they may appear empty at first glance, they are in fact rich with vital information about the universe's past, present, and future. These clouds are integral to the birth of stars and galaxies, and their study provides us with invaluable insights into the processes that shape everything around us. They are time capsules holding the secrets of the ancient cosmos, and as technology improves, our ability to learn from them grows exponentially. These discoveries don't just allow us to look back in time, they also provide clues about the future of the universe. By studying these clouds, scientists can learn how galaxies might continue to grow, how stars will form, and how the universe itself will evolve. We are not simply examining the past, we are learning about the forces that will guide the cosmos for billions of years to come, and how those forces will continue to shape the fate of galaxies, stars, and planets. In recent decades, the search for life beyond Earth has captivated the imagination of people around the world. For centuries, humans have gazed at the stars, wondering whether we are alone in the universe. With billions of stars scattered across the vast reaches of space, it seems almost inevitable that some of them could have planets like our own, where life might exist. For much of human history, this idea was pure speculation. There was no evidence to support the notion that other planets could harbor life. However, in the last few decades, this view has changed dramatically. Thanks to the development of powerful telescopes and space missions, scientists have discovered thousands of planets orbiting distant stars, known as exoplanets. This groundbreaking discovery has reshaped our understanding of the universe and our place within it, opening up new possibilities for the future of space exploration and the search for life beyond Earth. However, out of the thousands of exoplanets that scientists have discovered so far, only a select few seem to possess the right conditions to potentially support life as we know it. Despite the fact that the search is still far from complete, each new exoplanet discovery brings us one step closer to answering one of humanity's most profound and enduring questions. Are we truly alone in the universe? These planets, which orbit distant stars beyond our own solar system, are known as exoplanets, and they present a tantalizing glimpse into the vast diversity of worlds that exist in the cosmos. Exoplanets can be vastly different from the planets in our solar system, some bearing uncanny similarities to Earth, which sparks the possibility that they may host life. On the other hand, there are exoplanets that are massive gas giants akin to Jupiter, and some even defy all expectations, challenging our understanding of what planets are capable of. The field of exoplanet discovery has revealed planets with extreme and often bizarre conditions, many of which exist in environments so inhospitable that they seem almost otherworldly. For example, there are exoplanets locked in eternal winters, their surfaces perpetually covered in ice, while others are scorching hot, with oceans made entirely of molten lava. There are even planets where iron rains down from the sky. These extraordinary phenomena are caused by the intense heat in their atmospheres, which turns metals into liquid droplets that fall like fiery rain. Some exoplanets are so strange that they seem almost impossible to comprehend, yet their existence challenges and expands our understanding of what planets can be. The first confirmed exoplanets were discovered in 1992, orbiting a pulsar, a type of dead star that emits powerful beams of radiation. These early discoveries showed that planets could exist in places once thought inhospitable, defying expectations and broadening our vision of the universe. But it wasn't until 1995 that astronomers discovered 51 Pegasi b, the first exoplanet orbiting a sun-like star. This gas giant was a milestone, confirming that planets could exist around stars similar to our own sun and opening the door to an entirely new field of astronomical discovery. Since then, astronomers have identified over 5,000 exoplanets, and that number continues to grow with each passing year. The development of more advanced telescopes, such as the JAMES WEBB Space Telescope, has provided scientists with new tools to study the atmospheres of these distant worlds. This cutting-edge technology allows researchers to analyze the chemical makeup of exoplanet atmospheres, searching for signs of life and gaining invaluable insights into the nature of these far-flung planets. With each new discovery, we inch closer to understanding not only the makeup of these exoplanets, but also the possibility of life beyond our solar system. Exoplanets come in many different shapes and sizes, and scientists categorize them based on factors such as their mass, composition, and position within their respective star systems. One of the most important categories is gas giants, which are massive planets primarily composed of hydrogen and helium, the two simplest and lightest gases in the universe. These gas giants can be enormous, often many times larger than Earth. For instance, Jupiter, the largest planet in our solar system, is so massive that over 1,300 Earths could fit inside it. Gas giants like Jupiter and Saturn do not have solid surfaces. Instead, their outer layers are thick clouds of gas, which become denser and hotter as you move deeper into the planet. In fact, the pressure at the core of these gas giants is so extreme that hydrogen, a gas here on Earth, turns into a liquid deep inside the planet. Scientists suspect there may be a solid core at the center of these planets, but it remains impossible to confirm due to the difficulty of sending probes deep enough to reach it. Our understanding of gas giants, particularly those in our own solar system like Jupiter and Saturn, is largely thanks to their sheer size and visibility in the night sky. Their enormous size makes them easy to spot with telescopes, and they stand out even more because they emit more radiation than they receive from the sun, further highlighting their presence in space. This makes them ideal subjects for astronomers to study, both within our solar system and in distant star systems. In fact, many of the exoplanets discovered so far are also gas giants, and this is due in large part to the ease with which they can be detected. When a gas giant passes in front of its star, it causes a noticeable dip in the star's light, a phenomenon known as a transit. This allows scientists to study the exoplanet's size, atmosphere, and orbit, even from millions of light years away. While gas giants like Jupiter and Saturn are mostly made of hydrogen and helium, some of the exoplanets that scientists have discovered are even more unusual. For example, some are classified as hot Jupiters, a type of gas giant that orbits so closely to its star that it experiences extreme temperatures. Others are ice giants, such as Uranus and Neptune, which, although still gaseous, contain more water, ammonia, and methane than their gas giant cousins. The discovery of so many gas giants, both near and far, has prompted numerous exciting questions for scientists. What are the full range of conditions that gas giants can survive under? How do they form? And could life exist on planets with conditions similar to those found on gas giants? Even though gas giants may seem inhospitable to life, their study is critical for understanding the broader workings of the universe. By studying these massive planets, scientists learn about the processes of planetary formation, the dynamics of atmospheres, and even the conditions that may allow life to flourish in environments vastly different from our own. For all the questions that gas giants pose, they also offer vital clues about the fundamental nature of planets and the universe itself. Another fascinating category of exoplanets are those similar to Neptune, often referred to as mini-Neptunes. These planets, which share many characteristics with Uranus and Neptune, are smaller than the massive gas giants like Jupiter and Saturn, but still exhibit the same kind of gaseous makeup. To understand mini-Neptunes, it's helpful to first look at the larger ice giants in our solar system, Uranus and Neptune. These planets are known for their thick atmospheres composed primarily of hydrogen, helium, and methane, which give them their striking blue appearance. Their atmospheres also produce extremely strong winds and intense weather systems. Like Uranus and Neptune, mini-Neptunes are considered ice giants because their atmospheres and interiors contain significant amounts of water, ammonia, and methane ice. While these planets are smaller in size than their larger counterparts, they still have thick atmospheres made mostly of hydrogen, helium, and ice. However, mini-Neptunes lack the dense cores of gas giants like Jupiter, which means their atmospheres are not as thick, though they are still predominantly gaseous. The defining feature of mini-Neptunes is that, unlike Earth or Mars, they do not have solid surfaces. Instead, they are composed of a mix of gases and ice, and in some cases may have a rocky core at their center. While scientists have yet to directly study these cores, they have observed mini-Neptunes displaying atmospheric conditions resembling those of Uranus and Neptune, including clouds, strong winds, and dynamic weather systems. These similarities make mini-Neptunes appear as smaller versions of their massive cousins. Astronomers are particularly interested in mini-Neptunes because they are relatively common in other star systems. Studies suggest that mini-Neptunes may be among the most abundant types of planets in the galaxy. What makes them especially intriguing is the variety of atmospheric conditions they exhibit. Some mini-Neptunes have thick, cloud-covered atmospheres that trap heat, causing extreme surface temperatures, while others may have lighter atmospheres with a mix of gases and ice, leading to different kinds of weather patterns. Despite their similarities to Neptune, mini-Neptunes differ in significant ways, particularly in terms of their size and the dynamics of their atmospheres. Their smaller size means they may not have the same powerful magnetic fields or violent storm systems as their larger counterparts. But the potential for diverse and complex environments on these worlds remains a fascinating area of research. However, even though these planets may appear to be inhospitable at first glance, they can still harbor remarkably active environments, with weather patterns that could rival those on Earth and, in some cases, even hidden oceans concealed beneath thick, swirling clouds. The ongoing discovery and detailed study of Neptune-like exoplanets are offering scientists an extraordinary wealth of information about the possibilities of life beyond our planet. These studies provide essential clues about the conditions that could exist on distant worlds and deepen our understanding of how planets form and evolve. With advancements in technology, the future promises even greater revelations, allowing us to examine these faraway planets more closely, unveiling their enigmatic atmospheres, weather systems, and perhaps even evidence of life in ways we never thought possible. As space exploration technologies progress, new missions are being proposed to send probes to these distant worlds. The goal is to study these planets up close, revealing their hidden secrets and expanding our collective understanding of the universe. One fascinating group of planets that has captured the imagination of astronomers are the so-called super-Earths. These exoplanets are larger than Earth, but smaller than gas giants like Neptune or Jupiter. The term super-Earth refers specifically to their size and mass, not their composition or their potential to support life. While some super-Earths may have solid, rocky surfaces similar to our own planet, others may be enveloped by thick layers of gas or ice. What truly makes super-Earths so intriguing is the possibility that some of them might be capable of supporting life. If a super-Earth orbits its star at just the right distance, neither too close nor too far, temperatures could be conducive to the presence of liquid water. Since water is considered essential for life as we know it, these planets could potentially provide a home for living organisms, from microscopic microbes to more complex life forms. Yet it's not only the potential for life that makes these planets so captivating. Their sheer size also brings intriguing features to the table. With more mass comes stronger gravity, which would result in a noticeably heavier experience for any human visitors. Moving around on a super-Earth could be significantly harder than on our home planet. However, the stronger gravity might also come with an unexpected benefit, such as a thicker atmosphere, which could offer enhanced protection against harmful space radiation, possibly making such planets even more suitable for life. Super-Earths come in an array of fascinating forms. Some might be completely covered by vast oceans that stretch endlessly across the planet's surface, while others could have dense atmospheres thick with clouds, trapping heat and potentially creating extreme surface conditions akin to those of Venus. Still others might have rich mineral deposits or possess chemical compositions that are entirely unique and unlike anything found on Earth. Because of their larger size, super-Earths may also experience more active geological processes, such as frequent volcanic eruptions, which could help replenish and stabilize their atmospheres over long periods of time. If a super-Earth happens to have a magnetic field like Earth's, it could offer additional protection from the harsh effects of solar winds, making it even more Earth-like in character. Astronomers have already identified several super-Earths in distant star systems, many of which have generated considerable excitement. Planets like Kepler 22b and TOI 700d are particularly noteworthy because they lie within the habitable zone of their stars, where conditions may be just right for life to thrive. These discoveries mark only the beginning of our journey to understand super-Earths and their potential to host life. As telescopes improve and space exploration continues to evolve, the mysteries surrounding these worlds are sure to expand, opening up new frontiers in the search for life beyond our solar system. In our own solar system, the rocky planets, Earth, Mars, Venus, and Mercury, present a unique subset of worlds. These terrestrial planets, composed mainly of solid rock and metal, stand in stark contrast to the gas giants like Jupiter and Saturn, which lack solid surfaces and cannot support standing. This fundamental difference makes the study of terrestrial planets incredibly valuable to scientists, particularly those searching for signs of life beyond Earth. Of all the terrestrial planets, Earth is by far the most famous, being the only known world to host life. Yet the search for other rocky planets with the potential for life is a primary objective in the field of astrobiology. Mars, Venus, and Mercury have all attracted the attention of researchers eager to unlock their mysteries. Mars, in particular, has been a focal point for decades. This red planet features a rocky, barren surface marked by ancient riverbeds and dried lakes, evidence of a more hospitable past. Many scientists believe that in ancient times, Mars may have had the right conditions for life, and research efforts continue to explore its history. NASA has sent numerous rovers to the Martian surface, conducting tests to determine whether life ever existed there, and whether it might still be possible today. The evidence of past water on Mars has only fueled the debate about its potential to support life, either in its past or perhaps even in its present, deep underground. Venus, often referred to as Earth's twin due to its similar size and composition, offers a stark contrast to Mars. While both planets are terrestrial in nature, Venus is a nightmarish world of unbearable heat, with surface temperatures soaring high enough to melt lead. Its thick atmosphere, composed of toxic gases like carbon dioxide and sulfuric acid, creates a runaway greenhouse effect, making the planet's surface one of the hottest in the solar system. Despite this hostile environment, scientists remain intrigued by Venus. By studying its extreme conditions, researchers hope to better understand the processes that can lead to such a dramatic divergence from Earth-like conditions. Venus is, in many ways, a cautionary tale, a lesson in how a planet's atmosphere can dramatically alter its climate, turning it into a furnace incapable of supporting life as we know it. Mercury, the smallest of the terrestrial planets, lies closest to the Sun, and it presents its own set of mysteries. With no atmosphere to protect it, Mercury experiences extreme temperature fluctuations, boiling hot during the day and freezing cold at night. This makes Mercury an excellent place for studying the effects of space debris and impacts, as the lack of atmospheric protection leaves its surface exposed to the full force of the universe's impacts. Mercury's surface, which has been pounded by countless meteoroids over billions of years, provides valuable insights into the history of our solar system, as well as how planets and their surfaces evolve over time. All of these planets, Mars, Venus, and Mercury, share one key characteristic. They all have solid, rocky surfaces, which makes them unique compared to gas giants. This feature is crucial for scientists as they continue their search for other rocky planets outside our solar system. These planets are often located in a region known as the habitable zone, or Goldilocks zone, an area around a star where conditions are just right to allow liquid water to exist. The habitable zone is a critical concept for astrobiologists, as it is the primary area where life as we understand it could potentially arise. Why is liquid water so crucial for life? The answer is simple. Every living organism on Earth, from the smallest microbe to the tallest tree, depends on water for survival. If a planet is situated too close to its star, like Venus, it becomes too hot, and any water would evaporate, leaving the planet dry and barren. Conversely, if a planet is too far from its star, like Mars, the cold would cause any water to freeze, creating a frozen, lifeless world. The Goldilocks zone is where things are just right. Not too hot, not too cold, but ideal for liquid water to exist on the surface. If liquid water is present, the likelihood of life, however simple or complex, increases significantly, offering hope that somewhere in the vast expanse of the universe, another world might share our conditions, our oceans, and perhaps even our chance for life. Earth occupies a remarkable and truly rare position in the vastness of the universe. It lies in a perfect balance within what scientists call the habitable zone, or more colloquially, the Goldilocks zone. This unique location is not too close and not too far from the Sun, making Earth an extraordinary planet capable of supporting life. Its position allows liquid water to flow freely, forming vast oceans, meandering rivers, tranquil lakes, and even the clouds that drift across the sky. Water, in all its forms, is not just a defining feature of Earth's surface, but a vital ingredient for life itself. It nourishes, transports, and sustains countless species. Without water, Earth would not be the flourishing, vibrant planet that it is. It is this delicate balance of distance from the sun that makes Earth a rare gem among the billions of planets in the universe. A cradle for life, where water flows freely and conditions are just right for organisms to thrive. Think of Earth's position in the habitable zone as the story of Goldilocks. Everything is just right. Temperatures are moderate, allowing for a comfortable and stable environment in which life can exist. Too close to the sun, and Earth would be scorched by unrelenting heat, turning it into a fiery inferno. Too far, and it would be cast into a frozen wasteland where life would struggle to survive. This zone is not just a happy coincidence. It is a fine-tuned balance that allows Earth to be the life-supporting planet that it is. But Earth's position in the habitable zone is only one part of the story. Equally crucial to its ability to support life is its atmosphere, which acts as a protective blanket surrounding the planet. This blanket keeps Earth's temperature within a range that is conducive to life. The atmosphere, made up of a mix of gases, traps warmth from the sun, preventing the planet from becoming either too cold or too hot. Without it, Earth's surface would experience extreme temperature fluctuations with freezing cold nights and scorching hot days, conditions that would make life nearly impossible. This atmospheric shield is not just about temperature regulation. It also serves as a barrier against the harsh radiation from space, preventing harmful cosmic rays and solar radiation from bombarding the planet's surface. Oxygen is one of the most crucial gases within this protective atmosphere. It is the gas that sustains life as we know it, allowing organisms to breathe and thrive. But oxygen alone is not enough. Carbon dioxide, often seen as a harmful pollutant in large quantities, plays an equally important role in maintaining Earth's temperature. This gas is a key player in the greenhouse effect, a natural process that traps heat within the atmosphere and keeps the planet warm enough to support life. However, the balance is delicate. Too little carbon dioxide and Earth would be too cold, too much, and the planet would overheat, possibly making it inhospitable. Now, take a look at the moon, our constant companion in the sky. Unlike Earth, the moon has no atmosphere. This lack of a protective shield means the moon is exposed to the full force of space's harsh conditions. During the day, temperatures can soar to over 250 degrees Fahrenheit, and at night they can plummet to a chilling and 280 degrees Fahrenheit. With no atmosphere to regulate these fluctuations, the moon is a barren, lifeless rock. This stark contrast highlights the crucial role an atmosphere plays in maintaining a planet's habitability. In contrast, Venus, our sister planet in the solar system, offers a stark warning of what can go wrong when the balance is disturbed. Venus has an extremely thick atmosphere, composed mainly of carbon dioxide, which creates a runaway greenhouse effect. This process traps heat so effectively that the surface temperature on Venus hovers around 900 degrees Fahrenheit, hotter than the inside of an oven. The atmosphere is also laced with toxic gases, making the planet's surface a cauldron of extreme heat and poisonous vapors. Venus is a vivid example of how a planet's atmosphere, when too thick and dominated by the wrong gases, can spiral into a deadly and inhospitable environment. However, the story of a planet's ability to support life is not only about the composition of its atmosphere, it also depends on the presence of a magnetic field. Earth is fortunate to have a strong magnetic field, which acts as a giant shield, protecting the planet from the harmful radiation emitted by the sun. The sun constantly sends out waves of powerful energy known as solar radiation. Without Earth's magnetic field, these rays would directly strike the planet's surface, slowly stripping away the atmosphere over time. Without an atmosphere, there would be no oxygen to breathe, no protection from the heat of the sun, and no way for life to survive. It would be as if Earth were trapped in an endless, frozen desert. Mars, our neighbor in the solar system, offers a cautionary tale of what happens when a planet loses its magnetic field. Long ago, Mars had a thicker atmosphere and may have had the right conditions for liquid water to flow across its surface. However, without a magnetic field to protect it from solar radiation, the sun's powerful rays slowly eroded the Martian atmosphere, leaving the planet cold, dry, and barren. Today, Mars is a desolate, lifeless world with no oceans, no forests, and no signs of life. The loss of its magnetic shield is one of the key reasons why Mars could no longer sustain life. Earth's magnetic field, therefore, is not just a random feature. It is an essential life-preserving shield. Without it, Earth might have suffered the same fate as Mars, becoming a cold, lifeless world where survival would be impossible. This magnetic field is another reason why Earth is so special in the context of space. Even if a planet lies within the habitable zone, that alone is not enough to guarantee it can support life. One critical ingredient is liquid water. While frozen water might exist on some exoplanets, water must be in liquid form for life, as we know it, to thrive. Liquid water provides the perfect environment for chemical reactions, the foundation of life's building blocks. Without oceans, rivers, and lakes, life on Earth would have a much harder time surviving. This is why scientists are so focused on finding liquid water on exoplanets, planets that orbit stars outside our solar system. They look for clues that suggest the presence of water, whether in the form of oceans, rivers, or even underground lakes. Detecting liquid water is no easy task. It requires advanced telescopes and sophisticated technology to analyze distant planets' atmospheres, searching for the right conditions that would allow water to remain liquid. A planet that is too close to its star might have water vaporized into gas, while a planet too far might have it frozen solid. The search for liquid water is not just about finding water, but about finding the right conditions that could potentially support life. But it's not just about the planet itself, it's about the star around which it orbits. Not every star is capable of hosting planets that could support life. Stars come in all sizes, and the size of a star plays a crucial role in determining whether or not a planet in its orbit can have the right conditions for life. Larger stars burn hot and fast, using up their fuel in a matter of millions of years. A planet orbiting such a star would only have a short window of time before the star exhausts its fuel and dies, making it unlikely for life to develop. On the other hand, smaller, cooler stars burn much slower and can live for billions of years. But because they are cooler, they may not provide enough warmth to sustain liquid water on planets orbiting them. If a planet is too far from one of these stars, it may not receive enough energy to maintain liquid water, making it too cold to support life. The stars most likely to support life-bearing planets are those similar in size to our Sun. These sun-like stars have just the right balance of heat and stability, shining steadily for billions of years. This stability provides the time necessary for life to evolve and develop. It's this combination of the right kind of star and the perfect location within the habitable zone that makes Earth so unique, giving life the opportunity to flourish in ways that are still incomprehensible in the grand scale of the universe. Even stars that are slightly smaller than our Sun, known as K-dwarfs, stand out as promising candidates for hosting habitable planets. While these stars burn at a cooler temperature compared to the Sun, their energy output remains stable, and their lifespan extends for an extraordinary amount of time, making them ideal candidates for sustaining life across vast epochs. K-dwarfs burn their fuel more slowly, allowing them to shine for tens of billions of years, far longer than our Sun will. In contrast, the Sun is projected to last for about 10 billion years before it exhausts its fuel. For a planet to harbor life, the star it orbits must offer a reliable and consistent source of energy. Stars that are too massive burn through their fuel too quickly, while those that are too small may not generate enough warmth to maintain life-supporting conditions. Thus, stars like our Sun and slightly smaller K-dwarfs strike a harmonious balance, providing sufficient heat, stability, and longevity, all of which are crucial for life. However, the challenge in confirming the existence of exoplanets, planets orbiting stars beyond our solar system, remains significant due to the vast distances separating these distant worlds from us. Directly observing these planets is, for the most part, impossible with current technology. Instead, scientists employ an array of ingenious techniques to detect these distant planets, unlocking the mysteries of far-off worlds without ever laying eyes on them. By studying the way light interacts with these planets, or observing subtle shifts in a star's movement, astronomers can infer the presence of planets orbiting these far-off stars. These methods allow us to uncover the presence of planets, even those we may never directly observe, providing us a deeper understanding of the universe's immensity. One of the most widely used techniques is the transit method. This method allows scientists to detect exoplanets in a way akin to watching a small shadow crossing a bright light. The process begins with astronomers observing a star located far in the distance, often hundreds or even thousands of light years away from Earth. As the planet orbits its star, it occasionally moves directly between the star and the observer. When this happens, the planet causes a slight but noticeable dip in the star's light, momentarily dimming it. Although the dimming is subtle, it can be detected if the planet's orbit is regular. The amount of light blocked by the planet depends on its size and how much of the star's light it obstructs. By carefully tracking the star's brightness over time, scientists can detect this regular dimming pattern, which reveals the presence of a planet. From this dimming, scientists can also determine the size of the planet. Larger planets block more light, while smaller ones obscure less. NASA's Kepler Space Telescope has been instrumental in this effort. Kepler has spent years scanning the skies, observing the light from thousands of stars. Thanks to its data, thousands of exoplanets have been discovered, worlds that would otherwise remain hidden from our view. Each of these planets orbits its own star, many in far-flung regions of our galaxy. Through the transit method, Kepler has provided scientists not only with the knowledge of where these planets are, but also valuable details about their potential habitability, such as their orbital period and whether they lie within the habitable zone of their stars, an area where liquid water could exist. In some cases, the transit method even provides additional information about the composition of the planet. Follow-up observations can reveal whether the planet has an atmosphere, and if so, what it's made of, whether it's composed of rock, gas, or ice. Every time a planet transits its star, it adds another layer to our growing understanding of these distant worlds. Another method used by scientists to detect exoplanets is the radial velocity method, also known as the wobble method. This approach detects the tiny gravitational effects that an orbiting planet has on its star. As a planet orbits its star, the planet's gravity subtly tugs on the star, causing it to wobble just a little. While this wobble is so minuscule it would go unnoticed by the naked eye, it is detectable by sophisticated instruments that track the star's movement with incredible precision. As the star moves toward us, its light shifts slightly toward the blue end of the spectrum, and when it moves away, the light shifts toward the red. This phenomenon, known as the Doppler effect, is the same reason the sound of a car engine changes pitch as it passes by. By measuring these tiny color shifts in the star's light, astronomers can infer the presence of an unseen planet. This method is particularly valuable for detecting planets that are either too far away or too faint to be seen directly, even with powerful telescopes. The radial velocity method has already led to the discovery of hundreds, if not thousands, of exoplanets. It provides information about the planet's mass, its distance from its star, and sometimes even the strength of the gravitational interaction between the two. This technique essentially uncovers the hidden properties of distant planets without ever having to visually see them. Another rare but exciting technique is direct imaging. This method allows astronomers to take actual photographs of exoplanets, something that was once thought to be nearly impossible. The difficulty lies in the intense brightness of stars, which often overwhelms the faint light emitted by the planets orbiting them. It's akin to trying to plot a tiny, dim light in the center of a blinding spotlight. To overcome this challenge, scientists use specially designed telescopes equipped with advanced technologies to block out the star's light, allowing the much dimmer planet to be visible. This technique is not used every day due to its difficulty, but when it works, it provides invaluable insight. Direct imaging allows scientists to capture details about an exoplanet's size, atmosphere, and even surface conditions. It brings us one step closer to understanding whether these planets could support life, or if they share any characteristics with planets in our own solar system. Finally, the gravitational microlensing method is another powerful technique in the search for exoplanets. This technique relies on the effects of gravity, specifically the bending of light caused by a massive object, such as a planet, passing in front of a distant star. According to Einstein's theory of relativity, gravity has the ability to warp space and time around it. When a planet passes directly in front of a star, Its gravitational field bends the light from the star, making it appear brighter and larger than it actually is. This effect, known as microlensing, acts like a magnifying glass, allowing scientists to detect planets that would otherwise be invisible. What makes microlensing so powerful is that it can reveal planets that are far too faint or distant to detect using conventional methods. Often, planets that are too far from their stars or too small to be noticed by the other techniques can be found using microlensing. This method allows scientists to discover new planets that would otherwise remain undetected, expanding our knowledge of the universe. Each of these techniques, transit, radial velocity, direct imaging, and gravitational microlensing, gives us a different lens through which to explore the cosmos. Together, they are enabling scientists to uncover the hidden worlds of our galaxy, taking us ever closer to answering the fundamental question, are we alone in the universe? Gravitational microlensing, an intriguing phenomenon in astrophysics, offers a powerful method to detect even the faintest and most distant objects in the universe, including planets that would otherwise be invisible to our most sophisticated instruments. Unlike traditional methods of planet detection that rely on direct observation or radiation emissions, this technique exploits the warping of light caused by the gravitational field of a celestial body. In essence, when a planet passes in front of a distant star, the planet's gravitational field bends and magnifies the light coming from the star. This rare event acts like a cosmic magnifying glass, allowing scientists to detect objects that are millions, if not billions, of light years away. This process, while subtle and fleeting, is akin to uncovering hidden treasure in the vastness of space. The moment light from the star is altered, astronomers on Earth can use specialized instruments to measure the slight variation in brightness. This shift in the light's intensity provides vital clues about the planet, its size, distance from its star, and even its location within its own solar system. Gravitational microlensing has thus become not only a tool for planet detection, but also a gateway for exploring other exotic objects in the cosmos, such as black holes or strange cosmic phenomena, all of which could cause similar distortions in light. While the technique has been used to uncover planets in distant galaxies and far-reaching corners of the universe, its potential doesn't stop there. Planets found through microlensing often reside in distant and uncharted parts of space, offering astronomers an entirely new lens through which to explore and understand the cosmos. This approach has unlocked discoveries that, just a few decades ago, would have seemed impossible, expanding our knowledge of the universe in profound ways. The discovery of planets outside our solar system, known as exoplanets, is one of the most exciting fields of study today, as scientists search for worlds that might harbor the conditions necessary for life. One of the most exciting planets discovered through this technique is Proxima b, which orbits Proxima Centauri, the closest star to our solar system, located just over 4 light-years away. Proxima b resides within its star's habitable zone, an area where conditions might be right for liquid water to exist on its surface. However, scientists are still investigating whether Proxima b possesses a protective atmosphere, which would be crucial for maintaining life-supporting conditions. The existence of such a planet, so close to Earth in cosmic terms, provides hope that other planets with similar conditions might also be found within the relatively short distance of a few light-years. Similarly, the TRAPPIST-1 system, located about 40 light-years away, has captivated scientists with its 7 planets, 3 of which lie in the habitable zone of their star. These planets, which are roughly the size of Earth, offer a tantalizing possibility of liquid water, a key ingredient for life as we know it. The TRAPPIST-1 system has quickly become a focal point for the search for alien life, and scientists are closely monitoring its planets for signs of biosignatures, chemical indicators that could point to life. The discovery of TRAPPIST-1 and its potentially habitable planets has made the search for life beyond Earth more exciting than ever before, offering a glimpse of what could be waiting out there in the cosmos. Kepler 442b, another promising exoplanet, lies about 1,200 light-years away. This planet is located within its star's habitable zone, and its size and position suggest it might have the necessary conditions for life, such as a stable atmosphere and temperate climates. Often referred to as a super-Earth, Kepler 442b is considered one of the best candidates for habitability, with scientists eager to learn more about its potential to support life. Another noteworthy discovery is LHS 1140b, a rocky planet situated around 40 light-years away. LHS 1140b stands out due to its thick atmosphere, which could potentially harbor liquid water, making it another prime candidate in the search for extraterrestrial life. Its rocky surface suggests that, like Earth, it might have a solid foundation conducive to life. Each of these discoveries brings us one step closer to answering the age-old question, could life exist beyond our home planet? The tools available to astronomers have evolved drastically in recent years. The JAMES Webb Space Telescope, JWST, with its advanced capabilities, has opened up new avenues for exploring exoplanet atmospheres. By studying the light passing through the atmospheres of these distant worlds, scientists can detect the presence of certain gases, oxygen, methane, and carbon dioxide, gases that on Earth are closely linked to biological processes. Oxygen, for instance, is produced by plants. Methane is a byproduct of microbial life, and carbon dioxide is a key component of Earth's life cycle. Even though no direct evidence of alien life has been found yet, the discovery of thousands of exoplanets that could support life has intensified the search, leading many to believe that Earth might not be unique in the vast expanse of space. One of the most exciting aspects of the search for extraterrestrial life is the concept of biosignatures, chemical or physical markers that suggest the presence of life. These biosignatures can take many forms: unique chemical compositions, unusual atmospheric changes, or even physical structures like fossils. The field of astrobiology, which studies the potential for life in the universe, relies heavily on biosignatures to guide the search for life beyond Earth. Biosignatures are categorized into 10 major types, each offering a different form of evidence for life. Isotope patterns, for example, are produced when living organisms process elements like carbon and oxygen in ways that differ from non-biological processes. Chemical signatures might include the simultaneous presence of gases like oxygen and methane, which are highly reactive and should not exist together without some form of biological activity to replenish them. Organic molecules such as proteins and carbohydrates can be preserved in rocks or sediments, and biological minerals created by organisms in ways that differ from geological processes are another sign. Microfossils, tiny textures found in rocks, and macroscopic structures like fossilized coral reefs are other potential markers. Even changes in a planet's atmosphere over time, reflecting biological cycles like plant activity affecting oxygen levels, could point to life. While these biosignatures are promising, it's important to remember that not everything that looks like a sign of life necessarily is. For a biosignature to be reliable, it must meet 3 key criteria. It must be clearly associated with life, it must be stable enough to persist long enough to be detected, and it must be measurable with existing technology. Non-biological processes, such as volcanic activity or chemical reactions in rocks, can sometimes produce effects that resemble biosignatures, which is why scientists must carefully eliminate alternative explanations before concluding that life is involved. One particularly interesting clue might be the imbalance of certain gases in a planet's atmosphere. For instance, a planet that contains both oxygen and methane in its atmosphere presents a paradox. These gases would naturally react and cancel each other out over time unless something is replenishing them. This imbalance could indicate that life is present, providing a compelling reason to focus further on such planets in the search for extraterrestrial life. For a biosignature to be truly useful, it must remain detectable long enough to be found. Many of the byproducts of life, such as metabolic waste, are products of chemical reactions that occur within living organisms. Over time, these byproducts, along with physical remains like fossils, can be preserved and serve as evidence of life. Some fossils on Earth, dating back over 3.5 billion years, are still detectable today, showing how life's remnants can survive for immense stretches of time. With each new discovery, our understanding of the universe grows deeper, revealing a cosmos that may not be as lifeless and inhospitable as once thought. While we have yet to find definitive proof of extraterrestrial life, the hunt for biosignatures continues to offer tantalizing possibilities. Whether microbial or more advanced, Life may exist elsewhere in the universe, waiting to be discovered in the most unexpected places. The search for these distant worlds is far from over, and with each passing year, we move one step closer to unlocking the mysteries of life beyond Earth. However, for a biosignature to function as reliable proof of life, it must remain intact long enough to be detected by scientists. This is crucial, because the biosignature needs to endure over time in a form that is stable and identifiable using the most advanced technologies available. A biosignature that decays or changes too rapidly would be of little use in scientific studies, regardless of its potential significance. While this might seem like an obvious requirement, there are numerous scenarios where life could exist on another planet and still go undetected, simply because our current technology is unable to spot these faint, elusive markers. Each potential biosignature comes with its own unique challenges and limitations. One of the most intriguing examples of this is oxygen. On Earth, oxygen is predominantly produced through photosynthesis, a process carried out by plants and a wide variety of other life forms. Oxygen is also essential for many organisms to breathe, and its presence in a planet's atmosphere is a key indicator of life. The distinctive patterns of light that oxygen reflects across a broad range of wavelengths make it a prime candidate for detection. However, the mere presence of oxygen does not confirm the existence of life. There are non-living processes that can also generate oxygen. Take, for example, photolysis, a process where sunlight breaks down water molecules, resulting in the production of oxygen. This can occur on a planet that has lost most of its water, or in an atmosphere that contains few other gases capable of condensing into liquid form. Therefore, while oxygen might seem like a clear marker for life, distinguishing whether it is biologically produced or a product of natural non-living processes is one of the most complex challenges facing scientists today. This issue is compounded by the problem of false negatives. Situations where life may actually exist on another planet, but the signs of life are too subtle or too obscured to detect. This phenomenon represents a major hurdle for scientists, as even advanced telescopes and probes may not be equipped to identify life in all its potential forms. As the scientific community looks toward future missions that will be able to examine the atmospheres of exoplanets in greater detail, researchers are actively working to refine the technologies and methodologies required to uncover these elusive biosignatures. One of the most significant obstacles in detecting biosignatures lies in the resolution of the instruments themselves. If telescopes are not sufficiently powerful, they may fail to capture the subtle features that differentiate a genuine biosignature from a false positive. These subtle features are essential not just for confirming the presence of life, but also for ruling out other non-biological explanations. In addition, space-based instruments are often developed by large, diverse teams of scientists with competing research interests. As a result, these instruments must often strike a delicate balance between various objectives. This can mean that the ability to focus specifically on signs of life may be compromised in favor of studying other phenomena, such as the composition of distant stars or the dynamics of planetary atmospheres, which further limits the scope of our search for biosignatures. The study of Earth's ancient history offers scientists an invaluable opportunity to understand the types of chemical traces that living organisms, particularly microbes, leave behind. These traces, which are often preserved in rocks and sediments over millions of years, can provide insight into the conditions that supported life on our planet long before humans emerged. Several scientific fields, such as geochemistry, geobiology, and geomicrobiology, are dedicated to studying these biosignatures in order to identify whether life ever existed in samples taken from Earth and potentially from other planets. Some of the most important biosignatures include microfossils and stromatolites, which are layered structures formed by microbial life, as well as molecular markers known as biomarkers. The isotopic makeup of certain elements, like carbon, nitrogen, and hydrogen, is another key indicator that can reveal traces of life. For example, different sulfur and oxygen isotopes found in minerals may also provide clues about biological processes. Scientists can also look at patterns in the abundance and isotopic makeup of metals like iron, manganese, chromium, and various rare earth elements, as their concentrations can change in response to the environmental conditions shaped by life forms. One example of how these isotopic markers work is seen in the study of fatty acids. The specific types of fatty acids found in a sample can indicate which bacteria were present in the environment and thriving at the time. Long-chain fatty alcohols, produced by planktonic bacteria with more than 23 carbon atoms, serve as another example. Geochemists often refer to these as biomarkers, as they provide direct evidence of microbial life. In addition, straight-chain lipids like alkanes, alcohols, and fatty acids, ranging from 20 to 36 carbon atoms, are often found in soils and sediments, and can point to the presence of life from higher plants, such as those seen in peat deposits formed from plant waxes. Life itself is a vast and complex network of biochemical processes, leaving behind a variety of biosignatures such as nucleic acids, lipids, proteins, amino acids, and kerogen-like substances. All of these can be identified in ancient rocks and sediments. Microbes, in particular, play a pivotal role in shaping their chemical environment, often leaving behind markers that serve as clues to their existence. For instance, certain bacteria can create minute pores in carbonate rocks that are visible under a microscope. These pores, which look like inclusions, are distinct in their size, shape, and pattern, often appearing swirling or branching. These characteristics make them stand out from the ordinary fluid inclusions typically found in rocks, and serve as compelling evidence that microbial life was once present. Sometimes biosignatures can be subtle patterns or features that suggest the involvement of life, but it's crucial to remember that non-living processes can also create similar formations. The search for life, whether in the past or present, that often hinges on carefully studying the shape and structure of certain objects. The form and size of these objects can offer important hints about whether life once existed in a particular location. A well-known example of this is the ongoing debate surrounding the Martian meteorite ALH 84001, which has sparked one of the longest-standing controversies in the search for evidence of life beyond Earth. The meteorite contains what some scientists interpret as fossils of microscopic rock-like structures that resemble bacteria in their shape. These structures, if they were indeed biological in origin, could represent the first direct evidence of ancient life on Mars. This example highlights the challenges scientists face in distinguishing between biological and non-biological processes when searching for biosignatures. It is a reminder that the search for life, whether on Earth or on distant planets, is often more complex and nuanced than it might appear at first glance. However, as science continues to evolve, most researchers today believe that these structures are far too small to serve as definitive fossils of actual cells. From these ongoing debates, a common understanding has emerged. Relying solely on the shape and structure of an object, or its morphology, is not enough to prove the existence of life. Morphological analysis, while important, can often be subjective, and misinterpretations can lead to errors. In recent years, scientists have agreed that extraordinary claims, such as the discovery of past life, require far more than just morphological data to back them up. The interpretation of shapes alone is no longer considered a foolproof method for detecting ancient life forms. The search for evidence of life in the distant past is now based on a more robust approach. No single chemical or compound can definitively prove that life once existed. Instead, scientists now focus on identifying specific patterns within organic compounds that suggest life was involved in their creation. These patterns serve as subtle clues left behind by ancient life forms. For example, when cells break down, they leave behind certain lipids, fatty molecules that are distinctive and can be traced back to biological origins. These lipids, which are the remnants of cell membranes, exhibit a clear and recognizable pattern. They tend to be concentrated, consistent in size, and are made up of an even number of carbon atoms, all of which serve as a signature of their biological origin. Similarly, life forms tend to use only left-handed amino acids, another potential clue pointing to past life. This characteristic stands in stark contrast to non-living chemical processes, which do not follow the same pattern. These patterns, whether they are chemical in nature or magnetic in origin, are increasingly seen as essential biosignatures, markers that hint at the presence of life. Such signatures can appear in many forms, from the distinctive chemical traces left behind in rocks and petroleum to the unique magnetic signals that could reveal long-lost biological activity. Chemical biosignatures are particularly intriguing. These are complex organic compounds, molecules made up of carbon, hydrogen, oxygen, nitrogen, and sulfur, that are often found in substances like crude oil or petroleum. Over millions of years, these compounds undergo a slow transformation, breaking down into simpler forms. This process, often referred to as biochemical alteration, leaves behind a simplified molecular structure that can be traced back to its organic roots. The breakdown of organic matter from living organisms over time leads to the formation of chemical compounds with unique characteristics. For instance, compounds like pristane, steranes, and tropanes, which are often found in petroleum, are the result of chemical processes that use organic materials, such as plants, as their foundation. These specific compounds are critical to understanding the origins of petroleum. Tropanes, for example, come primarily from land-based flowering plants. By analyzing small amounts of these biomarkers within petroleum or its source rock, scientists can gain insights into where the oil originated, the conditions under which it formed, and how old it is. Specialized techniques such as gas chromatography and mass spectrometry are employed to identify and measure these compounds with precision. These biomarkers are so valuable that they are sometimes referred to as chemical fossils, as they provide a chemical record of the oil's history. By studying these compounds, geologists and chemists can trace the migration of oil deposits, determine the maturity of the oil, and even pinpoint the exact geological conditions that led to its formation. Biomarkers are incredibly resilient and resistant to environmental changes, which makes them useful not only for tracing the origins of petroleum, but also for detecting oil spills or contamination in waterways and lubricants. However, it's important for scientists to be cautious when analyzing untreated rock samples, as these may be degraded or contaminated over time, potentially leading to inaccurate conclusions. In the quest for life beyond Earth, the study of exoplanet atmospheres has become a key focus. These atmospheres are often seen as the most promising places to find signs of life, whether it's clues about a planet's habitability or specific biological markers. Over millions or even billions of years, life on a planet alters its chemical makeup in ways that are unique to biological processes. These changes cannot be mimicked by ordinary chemical processes alone. Earth's atmosphere, for example, is rich in oxygen and contains significant amounts of methane, two gases that are both produced by living organisms. The unique combination of these gases is one of the clearest signs of life on Earth. The color of an exoplanet or its reflected spectrum can also serve as an indicator of life. Life forms, especially those that use sunlight for energy, like plants, possess pigments that give off distinct light patterns. Scientists use Earth as a reference point when examining distant planets, often comparing how Earth appears from space with how other planets might appear under similar conditions. Furthermore, ultraviolet light can cause certain life forms to glow in a way that is visible from space, a phenomenon that new space observatories may soon be able to detect. Researchers have also made significant strides in detecting gases like hydrogen and methane in the atmospheres of distant planets. However, to properly interpret these findings, it is essential to consider the planet's environment and its underlying chemical processes. For example, finding both oxygen and methane together on a planet is a significant clue. This combination is extremely difficult to form naturally and would likely indicate a chemical imbalance caused by biological activity. The imbalance could be an indicator of life itself. Several gases have emerged as top candidates for atmospheric biosignatures. Dimethyl sulfide and chloromethane, for instance, are two chemicals that could point to biological processes occurring on a distant world. Another potential biosignature could be the pairing of methane and carbon dioxide in a planet's atmosphere. Scientists are also investigating the presence of phosphine in Venus's atmosphere, a gas that, on Earth, is often associated with biological processes. When the balance of gases in a planet's atmosphere appears unusual, it might be a sign that life is at work. On Earth, life has altered the atmosphere in ways that are unparalleled by any natural process. This disequilibrium is one of the key markers of life. Methane is a particularly intriguing gas in this context. On Earth, methane is much more abundant than it would be if it were solely a product of natural processes. This abundance is a direct result of living organisms constantly producing methane. On another planet, if methane levels are unusually high, it could point to the presence of life. However, it's important to remember that Earth is the only known planet with life, so we often look for signs of life based on the gases and substances we are familiar with. Life on other planets, however, could be very different, and it might still leave behind detectable markers. These are known as agnostic biosignatures because they do not rely on life being exactly like we know it. The search for life beyond Earth often hinges on the understanding that all life, no matter how strange or alien, requires a source of energy. This energy is typically derived from chemical imbalances, processes where some chemicals are more likely to gain or lose electrons, creating the conditions necessary for life to thrive. These imbalances are essential for life to survive. Geological processes, which are unrelated to life, help scientists determine what the natural chemical balance of a planet should be. When a planet's atmosphere strays from this balance, it could indicate the presence of life, a potential universal biosignature, even if the biology is completely unknown. Detecting biosignatures is an extraordinary scientific achievement, but just as important is the discovery that a planet does not harbor life. This is because life depends on redox imbalances, and understanding these imbalances helps scientists differentiate between a living and a non-living world. For instance, when certain chemicals are more likely to gain or lose electrons in a redox reaction, life can convert available resources into energy. However, if a planet has a redox imbalance with no life to take advantage of it, that is known as an anti-biosignature. While it doesn't point to life, it still provides crucial information about the planet. One fascinating hypothesis in the search for life is the polyelectrolyte theory of genes. This theory suggests that DNA, or similar genetic materials, must have a special structure to evolve through natural selection. In 2002, scientists Stephen A. Benner and Daniel Hutter proposed that for a genetic material like DNA to evolve on any planet, it must be a polyelectrolyte. This means that it should have repeating charged parts that enable it to function in water. Benner and others have even suggested methods for detecting this type of genetic material on planets like Mars, Enceladus, and Europa. Mars, in particular, has been the subject of intense debate when it comes to the search for life. The presence of methane in its atmosphere has raised questions. Methane is a tricky molecule because it breaks down easily in a planet's atmosphere due to sunlight and other processes. If there is more methane than would be expected from these processes alone, it might suggest an active source. Given that life on Earth is a major producer of methane, finding similar levels of methane on Mars could point to life, or at least to something intriguing happening on the planet. Since 2004, various spacecraft and ground-based instruments have detected methane in Mars's atmosphere. The levels detected range from tiny traces between 0.24 and 0.65 parts per billion to as high as 45 parts per billion in certain locations. These fluctuations in methane levels could offer clues about Mars's past, its potential for life, and the ongoing mysteries of this distant world. Recent measurements conducted by advanced instruments aboard the ExoMars Trace Gas Orbiter have yielded surprising and contradictory results regarding methane on Mars. These instruments failed to detect any methane in the Martian atmosphere, setting a new and significantly lower limit on its presence, estimated at just 0.05 parts per billion. This finding stands in stark contrast to earlier observations, reigniting the ongoing debate about methane's mysterious presence on the red planet. To add to the confusion, current atmospheric models that detail how chemicals break down on Mars cannot adequately explain the rapid and irregular fluctuations in methane levels, particularly its apparent appearance and disappearance within such short timeframes. This mystery surrounding methane on Mars has profound implications. To determine whether this methane could be a sign of life, Or, if it originates from purely geological processes, scientists would need to conduct more detailed investigations. A lander or probe equipped with a mass spectrometer would be ideal for this task, as it could analyze the carbon content in methane molecules. By comparing the amounts of carbon-12 and carbon-14 isotopes, scientists could discern whether the methane is biological in origin, much like how scientists on Earth identify methane produced by living organisms. Adding another layer of complexity, Mars's atmosphere is rich in carbon monoxide and hydrogen, molecules that could serve as fuel for certain types of metabolism. This suggests that energy exists on the planet, but only specific forms of life would be able to use it. Yet, despite the presence of these crucial molecules, no life seems to be taking advantage of them. This observation lends credence to the theory of an antibiotic signature, a marker that suggests the absence of life on Mars, or at least no detectable life thus far. Astrobiology, the study of life beyond Earth, is rooted in the notion that any signs of extraterrestrial life, if found, would likely be identifiable through biosignatures. A biosignature is any clue or chemical signature that could point to the existence of life, either in the past or potentially still today. For a biosignature to be meaningful, it must be something that life itself would produce, and ideally, it should be very unlikely that non-living processes could generate the same result. To confirm the presence of alien life, scientists must establish that a detected biosignature originates from living organisms and not from natural, non-biological processes. As with most groundbreaking scientific discoveries, the proof of extraterrestrial life, whether it existed in the past or is still alive today, will require time, evidence, and the careful elimination of all other potential explanations. Looking back to the 1970s, NASA's Viking missions to Mars were the first to attempt experiments specifically aimed at detecting biosignatures. The two Viking landers carried 3 experiments each to test for signs of life, including signs of metabolism. Unfortunately, the results were inconclusive, leaving scientists with more questions than answers. Today, NASA's Curiosity rover, part of the Mars Science Laboratory mission, is at the forefront of the search for life on Mars. Curiosity's primary objective is to understand whether the planet could have supported life in its distant past, and if life might still be possible under the right conditions. The rover is exploring the Martian surface using a range of sophisticated instruments designed to detect biosignatures. These tools can identify potential signs of ancient organisms, including microbial mats, organic molecules, or gases that could have been produced by living beings. The rover is particularly focused on areas where organic matter may have been preserved in the rock layers, which could increase its chances of finding fossilized remains of past life. Meanwhile, the ExoMars Trace Gas Orbiter, launched in 2016, continues to play a critical role in mapping the sources of methane and other trace gases in the Martian atmosphere. This mission is not only providing valuable data for understanding methane's elusive behavior, but it is also helping scientists pinpoint potential landing sites for the Rosalind Franklin rover. Scheduled for launch in 2022, the Rosalind Franklin mission aims to drill as deep as 2 meters below the Martian surface to search for biosignatures hidden beneath the harsh radiation of the planet's surface. Similarly, NASA's Mars 2020 rover, which launched in 2020, is dedicated to exploring areas that might have once harbored life. It is studying Mars' surface and geology to understand the planet's history, its past habitability, and whether any signs of life could have been preserved in the rocks. This rover is also tasked with collecting samples that may one day be returned to Earth for further analysis, offering the possibility of answering some of the most pressing questions about life on Mars. Looking beyond Mars, NASA's Dragonfly mission, scheduled for launch in 2025, is set to explore Titan, Saturn's largest moon. Titan is a particularly intriguing destination due to its thick, organic-rich atmosphere, which scientists believe could harbor the right conditions for early forms of life or prebiotic chemistry. Dragonfly will search for biosignatures in both Titan's atmosphere and on its surface, investigating whether life could have ever existed or may still exist on this distant world. Beyond Titan, one of the most promising targets for the search for life lies within our own solar system. Europa, one of Jupiter's smallest moons. Europa is considered one of the top contenders in the hunt for extraterrestrial life due to the strong evidence suggesting that beneath its icy surface lies a vast subsurface ocean. This ocean could potentially hold 2 to 3 times the amount of water found on Earth, providing a stable environment in which life could thrive. The Voyager spacecraft first observed Europa in 1979, revealing tectonic-like features on its surface that hinted at the presence of a subsurface ocean. In 1997, NASA's Galileo spacecraft detected changes in Europa's magnetic field, which scientists interpreted as evidence of a conductive layer beneath the surface, likely a salty ocean. In 2012, the Hubble Space Telescope captured images of Europa emitting plumes of water vapor from its surface, providing further support for the theory of a subsurface ocean. The Europa Clipper mission, scheduled to launch in 2024 and arrive at Europa in 2030, will carry advanced instruments to confirm the presence of this hidden ocean and study its composition. The spacecraft will also explore Europa's surface and search for signs of tectonic activity, potentially linked to the ocean beneath. Saturn's moon Enceladus shares many similarities with Europa, and although it has not been the primary target for biosignature searches, it remains an intriguing possibility. Enceladus is also believed to harbor a subsurface ocean. In 2005, NASA's Cassini spacecraft detected plumes of water vapor erupting from Enceladus' surface. Subsequent analyses revealed that these plumes contained salts and organic compounds, suggesting the presence of a deep, hidden ocean beneath the icy shell. Further measurements in 2014 strengthened the idea of a vast water reservoir, further increasing the moon's potential for habitability. While Enceladus has not yet been directly targeted in the search for life, future missions could be designed to investigate the possibility of life within its subsurface ocean. The potential for habitability on both Europa and Enceladus makes these moons exciting targets for future exploration and the search for extraterrestrial life. Far beyond our solar system, the search for life extends to exoplanets, planets orbiting other stars. The closest potentially habitable exoplanet is Proxima Centauri b, located just 4.2 light-years away. While this is relatively close in cosmic terms, it would still take more than 18,000 years to reach it using current spacecraft technologies. Because of this, our exploration of exoplanets for signs of life is limited to observation using powerful telescopes. So far, no definitive signs of life have been found on any exoplanet. However, research in this area is advancing rapidly, particularly with the launch of the JAMES WEBB Space Telescope in December 2021. While the Webb telescope cannot directly detect key gases like oxygen in the atmospheres of exoplanets, it can still help identify other potential clues, such as chemical compositions or atmospheric patterns, that might suggest the presence of life. In the coming years, new ground-based telescopes, such as the 30-meter telescope and the extremely large telescope, will allow scientists to study the atmospheres of exoplanets in even greater detail. These advanced telescopes will be capable of distinguishing between true signs of life and false positives, such as oxygen that could be produced by non-biological processes, bringing us one step closer to answering the age-old question: are we alone in the universe? One particularly intriguing object in space is the rogue planet, sometimes called a free-floating planet or isolated planetary mass object. These massive bodies possess the characteristics of planets, but do not orbit any star or brown dwarf. Instead, rogue planets wander through space alone, unbound by the gravity of a central star, unlike the majority of planets in the universe. Rogue planets can originate in various ways. Some are born within planetary systems, where they form just like regular planets, only to be ejected and sent drifting into the vast expanse of space. Others may form outside of a star system entirely, existing in isolation. As our technology advances and our understanding of the cosmos deepens, the search for life, both within and beyond our solar system, continues to evolve. From the methane on Mars to the icy moons of Jupiter and Saturn, and the distant exoplanets in faraway star systems, the possibility that life exists elsewhere remains an exciting and tantalizing prospect, one that future missions may soon bring closer to discovery. The universe, Vast and enigmatic, holds many surprises, but perhaps none as mysterious as the rogue planets that drift through the empty stretches of space. These wandering worlds, unbound by the gravitational pull of any star, have sparked intrigue and wonder among astronomers and stargazers alike. While much about them remains unknown, it is believed that such planets might never have belonged to any star system at all, forming independently in the cold, barren stretches of the cosmos. The Milky Way alone could be home to billions or even trillions of these elusive objects, drifting silently through the dark expanse. Recently, groundbreaking space missions like the Nancy Grace Roman Space Telescope are expected to offer more precise data on the numbers of these rogue planets. This marks a significant advancement in our understanding, bringing us closer to uncovering the hidden corners of our galaxy. What makes these objects particularly intriguing is the possibility that some of them may have developed in a manner similar to stars. For instance, the International Astronomical Union has proposed a new classification for such objects: sub-brown dwarfs. These are entities that form like stars but lack the necessary mass to ignite into full-fledged stars. Instead, they linger in the cosmic void, too small to shine, yet still possessing the characteristics of a much larger object. One particularly fascinating example of this category might be an object that was ejected from its original star system only to become a rogue planet. Alternatively, it might have formed independently as a sub-brown dwarf, free from the gravitational influence of any nearby star. Over the years, a variety of terms have been coined to describe these celestial wanderers, with phrases like isolated planetary mass objects, IPOs, and free-floating planets, FFPs, emerging as common terminology. These terms are still widely used in scientific literature, but in studies related to gravitational microlensing, the term rogue planet is often preferred. In media and press releases, however, these mysterious worlds may be described as wandering planets, starless planets, or simply free-floating planets. For example, in 2021, a series of press releases highlighted the discovery of over 70 rogue planets, using different terms to convey the nature of these objects. These discoveries sparked considerable interest in the scientific community, contributing to our ever-growing understanding of planets that live without stars. The first confirmed identification of an isolated planetary mass object came in the year 2000, when a UK-based team led by Lucas and Roos used the UK's National Telescope to spot IPOs within the Orion Nebula. That same year, a Spanish research team under Zapatero Osorio made a similar discovery in the Sigma Orionis cluster with the help of the Keck telescope. Both discoveries, confirmed through detailed spectroscopy in 2001, marked crucial milestones in the study of rogue planets. But this was not the beginning. As early as 1999, a Japanese team, led by Owasa, had found possible rogue planets in the Chamaeleon 1 cloud, though their findings weren't confirmed until 2004 by a US team using advanced spectroscopic techniques. Discovering these free-floating planets, however, is no easy task. Scientists employ two main techniques to identify rogue planets: direct imaging and gravitational microlensing. Microlensing has proven particularly effective in uncovering these celestial wanderers. In 2011, a significant breakthrough was made by astrophysicist Takahiro Sumi and his team at Osaka University. Working with collaborators from the microlensing observations in astrophysics and the optical gravitational lensing experiment, the team used telescopes in both New Zealand and Chile to survey 50 million stars in the Milky Way. Their observations led to the detection of 474 microlensing events, where the gravity of a planet bent the light of a distant star, revealing its presence. Of these 474 events, 10 were short enough to suggest that the objects responsible were planets, each roughly the size of Jupiter but without any nearby stars. From this, the team concluded that there might be nearly 2 Jupiter-sized rogue planets for every star in the galaxy. Some studies have even suggested that the number of rogue planets in the Milky Way could be as much as 100,000 times greater than the number of stars, though this would include many smaller objects than the giant Jupiter-like planets. In 2017, an even more extensive study was conducted by Priscilla Morrow from the Warsaw University Observatory. This study, 6 times larger than Sumi's 2011 research, suggested that for every star in the Milky Way, there might be at most 0.25 rogue planets the size of Jupiter or larger. But the real breakthrough came in September 2020, when astronomers used microlensing to detect an Earth-mass planet completely detached from any star. This planet, designated Ogle 2016 BLG-1928, represents a major step forward in our understanding of rogue planets and how they behave in the absence of stellar companions. While microlensing can reveal the size and gravitational influence of rogue planets, it doesn't provide enough information to understand their full nature or composition. To learn more about these celestial nomads, scientists turn to direct imaging, a technique that allows astronomers to capture actual images of these planets in space. Direct imaging, however, comes with its own set of challenges, particularly in determining the mass of these objects. To estimate the mass of a rogue planet, scientists must first understand its brightness and age. This can be difficult, especially since these planets are often located in regions of space far beyond our reach, where their ages are not easy to estimate. However, many of the IPOs discovered so far have been found in young star-forming regions, allowing astronomers to make more accurate age estimates. Most of the rogue planets discovered to date are relatively young, often less than 200 million years old, and are typically more massive than Jupiter, sometimes 5 times its mass or more. These objects are usually categorized as brown dwarfs of the L and T dwarf types. Some rare examples, such as the W dwarfs, are even colder and older, with masses ranging from 8 to 20 times that of Jupiter. One particularly intriguing candidate, Y08550714, lies just 727 light-years away, making it one of the closest known rogue planets of this type. These cold and distant worlds offer a unique opportunity for scientists to learn more about rogue planets, but accurate measurements and methods for determining their ages are still needed to unlock their secrets. The first IPOs discovered in the early 2000s were identified using direct imaging, particularly in young star-forming regions. These planets are thought to have formed in a manner similar to stars, which is why they are often referred to as sub-brown dwarfs. However, there is also a possibility that some IPOs formed in the same way as planets, but were later ejected from their original star systems. These ejected objects would exhibit different behaviors compared to those that formed in star-forming regions, with higher velocities and a lack of a surrounding dust and gas disk. Some of the older IPOs, such as YJ0832 plus 2837, are found to be traveling at speeds of up to 100 kilometers per second, suggesting they may have been ejected from their original star-forming region. Another object, WISE 1534-Nehedon-43, is moving even faster at around 200 kilometers per second, leading scientists to question whether it might be an exoplanet that was expelled from its star system. The exact origin of these rogue planets remains a topic of ongoing research and debate. Some scientists believe they represent the lower mass end of the star formation process, while others are not so sure. As technology continues to improve, our ability to study rogue planets will only grow, allowing us to uncover more about their formation and role in the broader context of galactic evolution. One thing is certain, however, most rogue planets are incredibly cold. Without the warmth provided by a nearby star, these planets are left to drift through space in perpetual darkness. Unlike the planets in our solar system, which bask in the light of the sun, rogue planets are isolated, living in the frigid void of interstellar space. And though their exact nature remains a mystery, each new discovery brings us one step closer to understanding these fascinating wanderers of the cosmos. However, even though these distant, wandering planets are freezing cold, they still manage to give off a small amount of heat. This heat is not something we can see with the naked eye, but it is there, detectable only through specialized technology. The kind of light responsible for this hidden warmth is called infrared radiation. You've probably felt this type of energy yourself. It's the warmth you sense when you stand near a hot object, even though you can't actually see the heat itself. In the universe, this same phenomenon happens on a far grander scale, and scientists have learned to harness this invisible energy to uncover the mysteries of space. To locate these wandering planets, Scientists rely on the most advanced telescopes we have, such as NASA's JAMES Webb Space Telescope. These telescopes are not your ordinary stargazing tools. They are meticulously designed to pick up on faint signals of infrared radiation, the heat that these distant planets emit. Unlike traditional telescopes, which primarily detect visible light, the light that our human eyes can see, the James Webb Space Telescope is equipped to observe infrared light. This is crucial because infrared radiation can pass through thick clouds of gas and dust that otherwise obscure objects in space, allowing the telescope to see what's hidden beyond these cosmic barriers. Through this advanced capability, astronomers can detect these elusive rogue planets, those that drift far from any star existing in the coldest, most desolate corners of the universe. Tracking these rogue planets is no easy task. They are lost in the dark, cold vastness of space, their faint glow often too dim for older telescopes to capture. Yet, with the heightened sensitivity of the James Webb Space Telescope, scientists have the ability to identify these far-flung planets, even if they are drifting alone, far from any source of light. The infrared radiation emitted by these planets is just a whisper in the vast cosmic expanse, but with the right technology, it can be heard. The James Webb Telescope's ability to detect this faint heat has allowed scientists to identify more of these mysterious wandering worlds than ever before. Beyond rogue planets, there are planets in our solar system that also give off detectable energy in the form of radio waves. Jupiter, for example, is known for producing incredibly strong radio waves. These waves are generated by Jupiter's massive magnetic field, an invisible force that surrounds the planet and influences particles like electrons. When these particles travel through the planet's magnetic field, they generate radio waves, which are a form of energy that propagates through space as electromagnetic waves. Jupiter's magnetic field is among the strongest in the solar system, far more powerful than Earth's. In fact, it is so strong that it traps high-energy particles from the sun. These particles then spiral around Jupiter, generating powerful radio waves, which, thanks to sensitive instruments called radio telescopes, can be detected from millions of miles away. Interestingly, it's not just planets like Jupiter that can emit these radio waves. Scientists believe that rogue planets, those without a star, might also produce similar radio signals. While these rogue planets do not have the warmth or light of a nearby star, they could still have magnetic fields strong enough to generate radio waves. If that's the case, these radio waves could provide an entirely new way to detect these wandering planets. Even though rogue planets don't emit visible light, their magnetic fields might allow them to communicate in the form of radio waves, which specialized radio telescopes can pick up. The great advantage of this is that radio waves are not blocked by the same obstacles that interfere with visible light. They travel through dust, gas, and other cosmic obstructions, making them an excellent tool for uncovering objects that are otherwise hidden. The radio signals from a rogue planet might be weak, but with the sensitivity of advanced radio telescopes, scientists can potentially detect even the faintest signals. This opens up an entirely new method of discovering planets, especially those that are far more difficult to detect with traditional optical telescopes. This breakthrough could revolutionize how we locate planets in our galaxy, uncovering a host of new, previously undetectable worlds. Moreover, detecting these radio waves could help astronomers understand more about the fundamental nature of planets, especially those that don't orbit a star. By studying how radio waves are generated by magnetic fields, scientists can learn about how these fields protect planets from harmful radiation. We already know that a planet's magnetic field plays a crucial role in shielding its surface from the sun's dangerous rays, and by studying rogue planets' magnetic fields, we could gain insights into how these planets survive without the protective warmth of a star. This information could prove invaluable in understanding the conditions required for life to exist elsewhere in the universe, whether that life exists on a planet with a star or on one that has been cast out into the cosmic void. But it's not just the planets that can experience such isolation. When a planet is ejected from its solar system, its moons could be affected too. Imagine a planet being hurled out of its original solar system only for its moons to remain bound to it. As the planet drifts through space, the moons travel alongside it, continuing their cosmic journey together through the darkness of the universe. While this idea may sound fantastical, it's entirely possible. Some moons may remain gravitationally tethered to their planets, traveling together through space as rogue planetary systems. However, not all moons stick around. The gravitational forces of massive objects, nearby stars, or even other large planets can sometimes disrupt the bond between a moon and its planet. When that happens, the moon is ejected from its planetary orbit, becoming a rogue moon. A rogue moon, unlike a rogue planet, is far more difficult to spot. Moons are much smaller, and unlike stars or even planets, they don't emit their own light. This means that rogue moons are essentially invisible to traditional detection methods unless they happen to pass near a bright star or planet. Without a light source of their own, rogue moons would be incredibly difficult to find, posing a significant challenge for astronomers in their search for new celestial bodies. The very possibility of rogue moons opens up even more questions. Could a moon, separated from its planet, somehow survive on its own in the cold, dark expanse of space? Could they harbor the conditions necessary for life, or could they perhaps serve as a refuge for life in ways we have yet to understand? While the discovery of rogue moons remains an enormous challenge, the pursuit of such objects is crucial. As technology improves and our telescopes grow more sensitive, the chances of finding these invisible wanderers grow ever more likely. And as we do, we open up new possibilities for understanding the universe, its planets, and the incredible journeys they undertake through the void. However, if rogue moons do exist, they could offer profound insights into the processes that govern the formation and destruction of planetary systems. The very existence of a moon that has been torn away from its parent planet and cast into the cold void of space suggests something far more chaotic about the universe than we previously understood. This phenomenon, in which celestial bodies are displaced by forces beyond their control, points to a cosmos that is not static or orderly, but rather a place of ceaseless motion and unpredictability. The forces at work on these moons, from gravitational interactions to cosmic collisions, show that even the smallest and most seemingly insignificant objects in space are subject to a dynamic, often violent environment. Rogue moons, in many ways, could be the silent, forgotten travelers of the universe, drifting through space without purpose or direction. Yet they carry with them the untold stories of the tumultuous forces that shaped their paths. These moons, severed from their parent planets, may harbor secrets that help us understand the volatile and unpredictable nature of our galaxy. Their existence forces us to reconsider our understanding of celestial dynamics and the fragility of planetary systems. Finding one, or even uncovering a system of rogue moons, would open an entirely new chapter in our quest to comprehend the cosmos. While rogue moons are an intriguing subject of study, it is the rogue planets that present an even more fascinating mystery. These planets, which do not orbit a star and instead drift alone through the vast, cold expanse of space, seem like unlikely candidates for the existence of life. At first glance, it seems impossible that such a planet could support life, as it is deprived of the warmth and light provided by a nearby star. However, scientists have speculated that under the right conditions, life could indeed survive on a rogue planet. For instance, if a rogue planet possesses a thick and dense atmosphere, it could trap heat from its internal energy, much like the heat retained within a planet's core. This trapped heat could keep the planet's surface warm enough to sustain liquid water, a crucial element for life. In fact, some rogue planets might even have vast, hidden oceans beneath their icy surfaces, much like the ones discovered on moons like Europa and Enceladus, which orbit Jupiter and Saturn. These subsurface oceans could provide a warm and sheltered environment where life might thrive, far away from the comforting glow of a star. The study of rogue planets also offers valuable insights into the nature of planetary formation and evolution. If a significant number of planets are ejected from their original solar systems, it suggests that the process of planetary system formation is far more chaotic and unstable than we once imagined. This revelation could dramatically shift our understanding of how planets and stars come into being, evolve, and ultimately meet their demise. These findings suggest that the universe is a far more dynamic and turbulent place than our previous models had indicated. Another exciting avenue of research involves the role rogue planets may play in unlocking the mysteries of dark matter. This invisible substance, which is thought to make up a significant portion of the universe's mass, has eluded direct detection by conventional means. However, some scientists hypothesize that the enormous gravitational pull of rogue planets could help shed light on this enigmatic phenomenon. Through a process called gravitational lensing, rogue planets might bend and distort the light from distant stars, allowing astronomers to study the effects of dark matter indirectly. This discovery could potentially lead to groundbreaking breakthroughs in our understanding of one of the most elusive components of the universe. In recent years, astronomers have made remarkable discoveries about rogue planets, furthering our understanding of these mysterious objects. In 2021, scientists made a groundbreaking find when they detected a rogue planet roughly the size of Jupiter, freely traveling through the Milky Way galaxy, far from any star. This isolated planet provided a rare opportunity for researchers to study the properties of a rogue planet up close, offering a glimpse into the unknown world of these wandering bodies. Then, in 2023, scientists uncovered evidence suggesting that rogue planets could actually outnumber stars in the universe. This revelation challenges previous assumptions about the way planets are formed and raises intriguing questions about the dynamics of our galaxy. It suggests that rogue planets may be far more common than we had previously thought, further highlighting the need for continued study of these enigmatic worlds. Looking ahead, exciting space missions are on the horizon that promise to unveil even more about rogue planets. The upcoming launch of NASA's Nancy Grace Roman Space Telescope, for example, is expected to provide astronomers with unprecedented insights into the existence and characteristics of rogue planets. With the help of cutting-edge technology and advanced observational tools, these missions could reshape our understanding of the universe over the next few decades, offering new clues about the formation of planetary systems, the nature of dark matter, and the potential for life beyond the stars. At the heart of these scientific inquiries lies one of the most profound mysteries in modern physics: dark energy. This invisible force, which is thought to make up roughly 68% of the universe, remains one of the most puzzling aspects of cosmology. Despite its enormous presence, dark energy cannot be directly observed or measured by conventional means. Instead, we infer its existence through its effects on the universe. Imagine for a moment standing in a room and feeling someone push you from behind. You don't see the person, but you can sense the pressure, the force, and the movement. In much the same way, dark energy exerts an influence on the universe, but we cannot directly detect its presence. The discovery of dark energy traces back to the late 1990s, when two independent teams of astronomers studying distant supernovae made a stunning observation. Supernovae are powerful explosions that occur when a star dies, and their light can serve as a standard candle to measure distances in space. When these teams measured the distances to a series of supernovae, they found something unexpected. The supernovae were farther away than anticipated. This meant that the expansion of the universe was occurring at a faster rate than previously thought. The key to this accelerated expansion, it turns out, lies in the presence of dark energy. Scientists believe that dark energy is responsible for pushing the universe apart, accelerating the expansion of space itself. This discovery was a pivotal moment in our understanding of the cosmos, challenging the long-held assumption that gravity was the only major force driving the dynamics of the universe. Today, dark energy is considered one of the most important and mysterious forces at play on a cosmic scale. But the question remains, what exactly is dark energy and how does it work? To begin answering this question, scientists have turned their attention to the very fabric of space itself. Far from being an empty void, space is thought to possess its own structure and properties. Some scientists have likened space to a stretchy fabric, which can expand or contract over time. As space itself expands, galaxies and other cosmic objects move farther apart. This expansion, which has been ongoing since the Big Bang, is driven by the mysterious force of dark energy. Unlike gravity, which pulls objects together, or the electromagnetic force, which causes opposite charges to attract, dark energy behaves in a completely different way. Instead of drawing objects closer, dark energy pushes them apart, driving the universe's continued expansion at an ever-increasing rate. Scientists often compare dark energy to the inflation of a balloon. As the balloon inflates, the points on its surface move farther apart. Similarly, as space itself expands, galaxies move farther away from each other. This process is ongoing and seems to be accelerating, driven by the enigmatic influence of dark energy. The discovery of dark energy has reshaped our understanding of the cosmos, but many questions remain. How exactly does dark energy work? What is its true nature? These are questions that scientists continue to grapple with, and with each new discovery, whether about rogue planets, rogue moons, or dark energy itself, we move one step closer to uncovering the secrets of the universe. The journey to understand these cosmic phenomena is only beginning, and the answers we find could transform our view of the universe in ways we have yet to imagine. However, dark energy exerts a repulsive effect on the universe. Instead of drawing galaxies toward each other, it pushes them farther apart. As the universe ages, the force of this repulsion grows stronger, accelerating the expansion of space itself. This phenomenon, which has become increasingly evident, challenges our understanding of the cosmos, because although dark energy is a dominant player in the universe's evolution, its true nature remains elusive. Scientists have been grappling with this enigma for decades, and despite multiple theories that seek to explain the force behind it, we are still far from understanding its origins and behavior. One of the first attempts to explain this mysterious force came from none other than Albert Einstein, who introduced the idea of a cosmological constant. This concept, which he initially used in his equations of general relativity, was part of his vision of a static, unchanging universe. However, when it became clear that the universe was, in fact, expanding, Einstein discarded the cosmological constant as a mere fudge factor. Despite this, the idea remained embedded in cosmological theory, and many years later it was resurrected to account for the phenomenon we now call dark energy. In the cosmological constant theory, dark energy is conceived as a constant force spread uniformly throughout space, unaffected by time. Imagine an invisible energy field that fills the vast expanse of the universe, never changing, never fluctuating. It is constant, persistent, and far-reaching, exerting its influence over the cosmic fabric. However, this theory does not account for all the peculiarities of dark energy, leading to the rise of alternative ideas. One such theory is called quintessence, which suggests that dark energy is not a static force, but one that evolves over time. Quintessence is a dynamic field, much like a magnetic field whose strength and direction shift depending on where you are in space and when you observe it. This theory implies that dark energy could behave differently at different points in time and across different regions of the universe, creating a much more fluid and adaptable understanding of the force. Some scientists even propose that dark energy may be similar to an energy fluid, constantly flowing through the cosmos, its intensity and effects varying across time and space. Yet there is another layer of complexity that researchers are exploring: the possibility that dark energy is linked to dimensions beyond the ones we know. In our everyday lives, we experience the universe as having 3 spatial dimensions and 1 dimension of time. But what if there are more dimensions, dimensions that we cannot perceive directly? Some theories suggest that the mysterious force of dark energy might be a consequence of interactions with these hidden dimensions, influencing the expansion of the universe in ways that we cannot yet detect. Another intriguing possibility is that dark energy could be related to a modification in our understanding of gravity, particularly on large scales. According to some theories, gravity may not behave exactly as we expect on a cosmic level. Perhaps it is weaker than we thought, or it behaves in ways that defy the assumptions made in Einstein's general relativity. In this view, dark energy is not an independent force at all, but rather an artifact of our incomplete understanding of how gravity works over vast cosmic distances. In this scenario, the apparent acceleration of the universe's expansion might be the result of flaws in our models of gravity. Despite the myriad of theories, studying dark energy is no small task. Its elusive nature makes it difficult to observe directly, but scientists have developed several sophisticated methods to probe its effects. One of the primary tools for understanding dark energy is the observation of distant galaxies and supernovae. By measuring the light emitted by these far-off objects, astronomers can calculate the rate at which the universe is expanding. The discovery of this accelerated expansion in the late 1990s through the study of distant supernova provided the first solid evidence for the existence of dark energy. Another key tool in the study of dark energy is the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB contains a wealth of information about the early universe, offering scientists a glimpse into the conditions that existed just moments after the birth of the cosmos. By studying the patterns and fluctuations in the CMB, researchers can learn more about the universe's overall structure and the role that dark energy may play in its continued expansion. One of the most ambitious projects designed to investigate dark energy is the Dark Energy Survey, DES, which aims to map the universe and study the effects of dark energy on a grand scale. By using advanced telescopes to observe billions of galaxies, scientists are collecting vast amounts of data to help answer one of the most profound questions in cosmology. What exactly is dark energy, and how does it influence the evolution of the universe? In addition to the DES, the European Space Agency, ESA, launched the Euclid mission, a spacecraft designed to study dark energy in even greater detail. The spacecraft will gather precise data on the shapes, sizes, and positions of galaxies scattered across the universe. By mapping these galaxies, scientists hope to uncover further clues about the nature of dark energy and its impact on the cosmos. The most captivating aspect of dark energy is perhaps its potential to shape the future of the universe. Since dark energy is responsible for accelerating the universe's expansion, it could lead to dramatic and even catastrophic changes in the distant future. If the influence of dark energy continues to grow unchecked, the universe could eventually experience a scenario known as the Big Rip. In this scenario, the expansion of space would accelerate so rapidly that galaxies, stars, planets, and even atoms would be torn apart by the ever-increasing distance between them. While this Big Rip is a far-off possibility, it remains a topic of serious consideration among cosmologists as they continue to study the properties of dark energy. On the other hand, if dark energy were to weaken over time, the expansion of the universe could slow, eventually halting and reversing. This could lead to the Big Crunch, a scenario in which the universe collapses back on itself, with galaxies, stars, and planets being pulled together by gravity in a cataclysmic event. As fascinating and terrifying as these possibilities may be, the truth is that we simply do not know what the future holds. The enigma of dark energy remains one of the most profound mysteries of modern science. It constitutes the majority of the energy in the universe, yet it remains undetectable and mysterious. Whether it is a constant energy field, a dynamic force, or the consequence of unseen dimensions, dark energy is central to our understanding of the cosmos. As technology advances and our tools for studying the universe improve, we may one day unlock the secrets of dark energy. Perhaps in the distant future, we will understand its true nature, how it came to be, and how it will continue to shape the destiny of the universe. For now, though, dark energy remains an elusive puzzle, one that we are only beginning to understand, but which holds the key to the ultimate fate of everything.